You know the feeling of making something with your own two hands? The joy and satisfaction it brings you. That is what pushes me forward to do more.
Like I found myself, my passion for technology.
Hi everyone, we'll just wait a couple more minutes for the others to join us. Thank you for your patience and your cooperation. And before we get started, I kindly ask you to turn off your audio and video so we can keep things running smoothly.
When I first walked through the college gate, I never really knew what to expect. There was so much confusion and unfamiliarity. Yet, there was a certain sense of excitement, of experiencing something new, something different. Looking at these new faces, those smiles and chit chats, I knew my life is gonna change. Learning something new ignites a fire in us. Here, we are encouraged to think out of the box and understand concepts that are taught out of the class. We can sit together, discuss with our friends, and clear our concepts. This way, we can ignite this fire more and more daily.
For a young maker like myself, labs like these helped me start my journey into the world of technology. I fell in love with what I learned, and the sheer thrill of seeing the concepts come to life is just like nothing else.
I know. The things you learn while actually involving in the process and doing things for yourself helps you understand, connect the dots, and remember so much better.
You know the feeling of making something with your own two hands? The joy and satisfaction it brings you. That is what pushes me forward to do more.
Yeah, it has given me happiness and confidence. Like I found myself, my passion for technology.
I just love colors. Every time I paint, I feel powerful. It is a form of expression for me, almost therapeutic. Here, I have always been encouraged to cultivate and harbor this artistic side of mine. And it's not just art, but music, dance, photography, and much more. Here, we get the space to explore all our passions.
College teaches you to see beyond your capabilities, to visualize the unthinkable and catch the unachievable. Life gives you certain opportunities to build your life, but college gives you the platform to live your life. Here, we share our memories, our stories, and our happiness. And it's a roller coaster of emotions. And before you know it, you'll realize that they have turned from friends into family. It isn't always about books, labs, and assignments. Academics are important, but there's definitely more to education than that. It's about finding yourself, about who you really are. It's about carving your own path. In this process of learning and growing, you build your own future. And then by the time it's all over, you realize that you're yet to explore so much more. What seems like the end is just a beginning. Come, find your beginning with us.
Namida, let's start.
Good evening, everyone. I am Namita Anakoshi, scholar at SJCET PALAI, and I'm delighted to be part of today's session, hosted by the esteemed AICTE Training and Learning Academy online faculty development program. Our theme for this event, Next Gen AI, Innovations in Machine Learning, Deep Learning, and Generative Models, is both timely and vital as we explore cutting edge advancements shaping the future. The Department of Artificial Intelligence and Data Science of St. Joseph's College of Engineering and Technology, PALAI, is honored to host this prestigious event. I extend my sincere appreciations to the organizers for their meticulous planning, the participants for their enthusiastic engagement, and the esteemed faculty for their unwavering support in making this program a success. To begin, I warmly welcome all the distinguished participants joining us from across the country. Your dedication to advancing your expertise is truly inspiring. A special mention goes to your esteemed faculty member, Assistant Professor Elvin Kurula from the Department of Artificial Intelligence and Data Science, who is chairing today's session. His guidance and expertise plays a vital role in ensuring the success of this program. Thank you for being with us. I welcome Professor Elvin to officially start this program and introduce our speaker for the session. Over to you, sir.
Thank you, Namita. It's my great pleasure to introduce our distinguished speaker for today's session, Mr. Abhimanyu KS, a senior software engineer and a renowned expert in artificial intelligence. With over a decade of experience in deep learning, machine learning, and generative AI, he has constantly pushed the boundaries of innovation in the field. Mr. Abhimanyu's professional journey is nothing short of inspiring. Starting his career in procurement roles, he transitioned in the world of AI, became a leader known for his groundbreaking contributions. His research and projects have had a tangible impact on the industry, including developing an in-house transfer learning tool that transformed NVIDIA Toolkit into a no-code platform, creating a log analyzer application using advanced AI models to efficiently resolve embedded system errors, delivering AI solutions for smart parking, advanced driver assistance systems, and crack detection in computer vision, designing generative AI tools, including YouTube summarization models and demand forecasting systems. His global expertise includes a stint in Japan, where his exceptional work earned him a perfect 10 out of 10 customer satisfaction score and accolades like the On the Fly Award for consecutive years. As a mentor at the ICT Academy of Kerala, he is also deeply committed to nurturing the next generation of AI professionals. Currently, Mr. Abhimanyu is at the forefront of generative AI, addressing complex problems and creating innovative solutions for real-world challenges. Today, he will enlighten us on recent advancement in generative AI, providing insights into the cutting-edge technologies shaping the future. Please join me in extending a warm welcome to Mr. Abhimanyu KS with a big round of applause. Mr. Abhimanyu, we are delighted to have you with us. The stage is all yours. Thank you.
Thank you, Elvin sir. I hope my voice is audible.
Yes, sir. Yes.
Yeah, okay. Okay, thank you. So thank you. Good evening, all. Good evening. I hope everyone can hear me loud and clear. Are we good to go?
Yes, sir.
Yes, sir.
I don't think everyone else is having a good evening because I'm seeing only few responses in the chat box. Even people are not willing to unmute and speak. Let's say that I'm actually planning to keep this session as a very interactive one. So please feel free to unmute and speak when and where you're getting any kinds of confusions or doubts, anything like that. So before starting of the session, I just wanted to ask Elvin sir. So please just be honest. How much portion of the introduction was taken from ChatGPT?
So it's actually completely from the ChatGPT, giving your CV into this ChatGPT and generating the
Yeah.
introduction.
Thank you, sir. Thank you for being honest. Actually, that is, I hope everyone these days would be using ChatGPT. Like, if you all remember, like in around 90s or start of 2000, if a person knows everything, we used to tell them like, okay, he's an encyclopedia of that information. Then come 2000, with the advent of Google, everyone what switched that phrase to what he's a Google. You can go and ask him anything, and you'll get all the answers. And right now, recently in one of the movies that released over here, they're using like he's having answers to all the questions. He's a Chat GPT. So that is how Chat GPT is what getting into our lives these days. Okay. Once again, thanks, Elvin sir. Okay. So again, one more time. Okay, good evening, all. I hope everyone is doing fine. Okay, so that was very nice introduction Elvin sir has given about me, and he has actually used one term like expert in something. I actually don't prefer to call me as an expert on anything because I believe all these kind of terms are relative. Okay, like some person could be more expertise than me in the field of AI. At least many of you are in this lot are more expertise than me in the field of AI as well as machine learning. Okay, so yeah, and I just want to give a very quick what agenda, like how we'll be going forward with the session. First of all, I don't know how many of you might have observed this. Like for the past 3 to 4 days, there were sessions happening for everyone in the field of AI. Okay, so you all might have observed this, right? All the other sessions that you had, or all the some of the sessions that is going to happen next, like the session that is going to happen immediately after this one, as well as the session that is planned for tomorrow evening. These are all taken by PhD holders. And I'm the only one in this lot who is actually not a PhD holder. So please don't expect any kind of scholarly definitions for most of the things that we discuss over here. And as you might have heard Elvin sir saying that I'm actually a mentor at ICD Academy of Kerala, which is actually an academy undertaken by government of Kerala to pass on courses on AI as well as machine learning. So I used to teach some of the students who are actually passed out from engineering colleges, or some people who are actually wanting to change their fields in the field of to the field of AI and all. So I used to keep my explanations, everything so legible that it could be understood for layman. So that's something that I have to tell at the very beginning. Please don't expect any scholarly definitions throughout the session. And the next thing is there is no PowerPoint deck. Okay, there is no PowerPoint deck. So the reason, because as I said, I used to take classes, and if we are taking any sessions with a PowerPoint deck, there'll be at least 10% of the audience believing that, okay, anyway, we are going to get the PowerPoint deck, so we don't have to pay attention to this. We'll just go to the PowerPoint deck once we receive that. So I don't plan my sessions like that. I'm very sorry about that. So there is no PowerPoint deck. Okay, instead I use a writing pad, and I'll be explaining things in the whiteboard. Okay, so please be vigilant and you can take notes on it. And as I said, if you're getting stuck anywhere, or if you're getting any kind of questions anywhere, please feel free to ask, and mute and ask. We'll clear it and go forward. And I've been told that this lot is a mixture of people who has some kind of an experience in coding, as well as there are some people who are not that exposed to coding. Um, because I plan to have what a notebook coded through in throughout meets when we are taking the session, but I think I'll just keep it aside for today. Okay, so I'll start sharing my screen once again. Are we good to go? Everyone settled, right?
Yes, sir.
Yes, sir.
Yeah. Okay. Thank you. And please don't address me as sir, because as I said, you are the people who are teaching students. I am not actually not that kind of teacher. Just address me by my name, please. Okay. Okay. So I hope my screen is visible, right? Is it visible?
Yes.
Is my
Yes, it's
yes. Okay. Okay. So for the past 3 to 4 days, I believe, like I said, you were having so many sessions on AI, machine learning, deep learning. There were so many concepts discussed and all. Can anyone tell like what is the core thing? What is the core thing that is happening in AI? Or what is actually AI doing? Anyone? Just uh, feel free to give your perspectives. Okay, there is no wrong perspective. Okay, if it is wrong, then we'll correct it. And anyone? What is actually happening in AI? What is basically what is this AI doing, or basically what is machine learning or deep learning? What basically what it is doing? Please feel free to unmute and speak.
it's
We
basically
Yeah.
with AI,
making everyday tasks easier.
What? I didn't get that.
we trying to mimic the human intelligence without emotions with the help of mathematics.
Okay. Human intelligence. Yeah, with the help of maths. Yeah, that's good. That's correct. Yeah. Anyone else? Any other?
AI is mimic human behavior.
Okay.
The uh, machine is learning using supervised and unsupervised reinforcement algorithms.
Yeah, correct. Okay. Supervised, using supervised and
And then
unsupervised. Okay.
deep learning, neural networks. And then
Oh,
language models, transformer
yeah.
models.
Okay.
So we are developing applications, AI applications using algorithms.
Okay. Okay. Pretty much. Yeah, we are around somewhere over there. Okay. Any other perspectives on what is this AI? Fundamentally, what is this AI
Sir,
doing? Yeah.
emulating human reasoning, the ability of humans to reasons,
Yes,
human
correct, correct.
reasoning.
These see, yes, yes. Yeah, pretty. I don't know. Maybe the lot is because maybe this audience is what basically scholars. That is why I'm getting very what deep level answers. I was actually looking for the very what a fundamental instinct, like fundamentally, what is AI doing?
Automation of mundane tasks by learning from patterns in the available data.
Yes, correct, correct. Learning. What was that? What was that? Learning. I didn't get
Learning
that.
from the patterns in the data available.
Learning from the patterns. Yes, correct. Learning from the patterns. Okay, so basically what does it mean? Basically what does it mean? So uh we have an input x, we have an input x. For all the input x we'll have an output y. Okay, so fundamentally what AI is doing,
Is a
AI is
function.
just finding this function. Yes, correct.
Function.
Finding the function that satisfies this equation.
Equation.
And yeah, and most of the time this function would be a very complicated.
Linear or
No,
non-linear.
yeah, it could be linear at sometimes, but most of the time it is very complicated
Is a
functions, and
complicated function.
that is the main reason why we have to depend on deep learning for most of the use cases and all. Okay, so fundamentally what AI is doing, AI is just trying to identify what is a function that satisfies this equation. Okay, so I hope everyone is clear with that. Now, I don't know how. Okay. I would request everyone to be unmute, be on mute. There is some noise from the background. Okay. If you're having any doubt, please feel free to unmute and speak. Okay. So I hope everyone might be familiar with Tesla, right? What is Tesla?
Manufacturer of self-driving cars.
Okay. Okay. I hope you all might be familiar to the person called as Tesla too, right?
Yes,
Yeah.
Nikola Tesla.
Yeah. Yes. So there is a very interesting quote from Tesla wherein he says that if you want to crack the secrets of this universe, if you want to crack the secrets of this universe, you have to think in terms of energy, frequency, and vibration. Okay. If you want to crack the secrets of this universe, you have to think in terms of energy, frequency, and vibration. Let's focus on this term frequency over here. In the context of time, what is frequency? What is frequency?
To time.
Sir,
Yeah,
it's
Inversely
a number of
proportional to 1 by 3.
We can say it
Is
like what?
basically
Inversely
number of
proportional to T.
number of
Yeah, we can say,
iterations
yes,
of a
correct. We can,
particle in terms of
Number
time.
of cycles per second.
yeah, that is actually all these definitions. What are in the context of physics? If you're put into a more general context, we can say that a repeated happening of an event over a period of time.
Event.
Okay.
Yes.
Repeated happening of an event. Repeated happening of an event over a period of time. Okay, which could be said as what? Frequency. Now, everything in this universe that is actually what repeatedly happening, it leaves a what? It leaves a pattern. It leaves a pattern. And machine learning, deep learning, or AI for that matter is to crack this pattern. I hope many of you might have seen this image. Just a second. There is an interesting image where you can see that this is actually the picture of sunrise taken at the same location at the same time for 12 months. Okay. And you can see that there is a pattern. I hope it is visible, right?
Yes, sir.
Yes. Yes.
Yes, sir.
Okay. So a pattern could be seen over there. It's somewhat like a what? A sine wave, right?
Yeah.
In the same way, everything that is what repeatedly happening over a period of time leaves a pattern, and our job as AI enthusiasts is to crack that pattern or to find that function. Now, when I say that everything in this universe, that what everything in this universe leaves a pattern, that includes our social media usage too. I hope many of you, at least once, many of you might have noticed that when you're scrolling through Instagram, there will be some reels that could be closely related to whatever things that is happening in your life, and you'll feel like, oh, like, okay, this reel is what I can relate to this reel. This is happening in my life. Has anyone faced like that a situation?
Daily, sir.
Yeah, right. So you will be scrolling through some reels you'll find it like, okay, this is what is happening in my life. I don't know how it is coming in front of me. Okay, so such kind of things is happening because they have actually cracked the pattern of your usage. Okay, how you use this Instagram or any kind of social media for that matter, how you are using it, how much screen time you are spending on specific post. Those kind of activities are being tracked, and based on that, they are actually retraining the model on a daily basis. Okay. Now, I don't know. Some of you might remember that around 2013, 2014, there was actually a challenge happening in the Facebook, which was like hash 10-year challenge. And this is basically a challenge wherein we post a picture of ourselves 10 years before and post a picture of how we look now. Has anyone participated in that kind of a challenge? like how we looked 10 years before and how we are looking right now.
Yeah.
Yeah, some of you might have. Okay. So
Yes, sir.
this 10-year challenge, this is actually a event that has been started by Facebook or Meta, okay, to collect the data, to collect your pictures. Okay, so eventually what they did is that they just tracked down this entire hashtag. They just tracked down the post having this entire hashtag and collected the images of how people looked 10 years before and how they are looking right now. And with that, they have actually trained a model, trained a AI model. And that model is a very, what, it plays a very
AlexNet.
basic, yeah, correct. AlexNet is, AlexNet, we can say that it is actually a very, uh, it could be said as a very base model on that. Okay. Apart from that, actually, I'm saying for this specific application, like how we looked before 10 years and how we are looking right now, they have actually what collected the data and created a model, and that model is what is actually paying a base for all these age generation apps that you see right now in Instagram and all other applications. I hope at least once you might have tried this kind of application wherein you what just increase your age and see how you will be looking when you are around 70 years old or 80 years old, right? Has
Yes,
anyone
sir.
tried out that? Yeah, fine.
Yes, sir.
So this is how this is how this kind of what data collection is happening in real time. And one more thing, uh, when we are actually discussing about AI or generative AI, we should definitely discuss about data. Okay, because you all know data is a core thing that is being what is playing a pivotal role in this kind of models, and we have to have a thorough understanding of how our data is being collected, because many of the time what we have seen is like I don't know, some of you might have installed some, like for example this age generation application. Okay, so you might be what downloading this application, and when you are installing it asks for certain permissions, including a permission to your gallery. So when you might be thinking that okay, it is just for what, just for uploading a photo so that it could generate what old looking photo of ours, but not that. When you're giving access to the gallery, when you're giving access to any application to your gallery, please keep in mind that there is a high chance of your entire photos or entire videos in the gallery to be gone to the database of that application. So such kind of thing we are actually not paying that kind of an attention these days. Okay, and if you really want to know like how the data is being, how our data is being collected, or how our data is being used against us for manipulating us, you have to, there is a very interesting docu-fiction in Netflix which is called as The Social Dilemma. You can watch it. It is a very interesting what a docu-fiction wherein it says like how these tech giants like Google, Facebook, or Apple, how they collect our data and how they are using it to manipulate us. Okay, that is a very interesting documentation. Please do watch it when you are getting time. Okay, so now let's get into the matter. That was all about the introduction. Okay, so we were actually talking about data. So I hope you all might have heard about this term like data is the new oil, right? Yes or no? Data is the new
Yes, sir.
oil.
Yes,
I
sir.
hope at least some of you might have exposed to this kind of a what a WhatsApp forward during 2016-17 when Geo was introduced. Why did Reliance name their data service company as Geo? Anyone knows that? Why did they name the company as Geo? So the word Geo is actually a mirror image of the word oil, right? And Reliance as a company, they started from oil, and they are saying that they have reached, they are actually taking up the new oil. And what is the new oil? New oil is the data. Now, if data is the new oil, okay, if we have an oil, we have to use this oil in some kind of engines. Okay, if data is a new oil, where are we using this oil? We are using this oil in the engines called as machine learning and deep learning. Now, if machine learning and deep learning are the engines, these engines must drive a vehicle. These engines must drive a vehicle. And the engine, machine learning and deep learning, these engines drive the vehicle, which is called as artificial intelligence. Okay, and to this scenario, the very recent addition or the researchers have added one more engine, which we call as generative AI. Okay, so I hope you're getting this analogy. Like there can be what confusions, like what is the difference between machine learning, what is the difference between deep learning and generative AI, what is happening in it. Okay, so I hope right now you get some kind of a what difference. And there is one more term which we call as data science. Can anyone tell then what is data science? Data science.
A discipline in which certain inferences are drawn from the available data by performing certain operations on the same.
That is actually what similar to machine learning, right? We are what drawing some.
So it is basically the science to understand the data that is available.
Yes, correct. It is basically the science to understand. Okay, or we can say with this analogy, we can say for every vehicle, there are some laws of physics to govern its movement. In the same way, the laws that govern this vehicle, AI, is what we call as data science. Okay, so I hope that is clear. Now, can anyone tell me what is the core difference between machine learning and deep learning?
The number of layers of neurons in the network.
Deep learning is subset of machine learning.
Okay. Anything else?
Section. Sir, am I audible?
Yeah.
Sir, in machine learning, feature extraction and classification, they need manual interaction in between. मतलब manual task भी होता है उसमें. And in deep learning, it is automated. Classification and feature extraction.
Yes.
In machine learning, data set is limited, but in deep learning, the data set is very large. Their layered architecture is used for solving complex problems. Here, simple problems we can solve by using machine learning.
Yes. Okay. So I think then what is the use of we are having these two different streams? Like we are having one stream as deep learning, we are having one stream as machine learning. I hope. I think yesterday actually I got a chance to be in the session that happened yesterday, just to have an idea like what is being discussed on yesterday's topic, so that I could carry on from there. And actually, I hope you might be remembering that there were several problems that was done to identify the sentiment of a what sentence, right? Whether the sentence is a positive sentiment or a negative sentiment, right? So basically, how was it done? How was it done? You trained a deep learning model for it, right? You trained a deep learning model for it, and this deep learning model, what? This deep learning model, when you're feeding a sentence, this deep learning model tells that whether this is a positive sentence or negative sentence, right? Yes or no? I hope you recollect yesterday what you did.
Yes, sir. Yes.
Yes.
Yes, sir.
Okay. So let me just open up ChatGPT over here. Okay. Now I hope everyone knows that ChatGPT is a generative AI model, right? There is no what contradiction to that. I hope there is no difference in opinion on that. Okay. So let's just look like if I don't know how many of you have tried it. Like if you're passing a sentence, if you're passing a what a positive comment to ChatGPT, will ChatGPT be able to tell us whether it is positive or negative?
Yes.
Yes,
It does
right.
actually, sir.
Yeah, so I don't have to show it, like it is taking some time to load. So if ChatGPT can tell that, or we can say that if generative AI can do that, okay, if generative AI can classify whether a sentence is positive or negative, then why do we need deep learning? Can't we do everything using generative AI?
For image-based datasets, deep learning is the preferred mode. That's why.
I hope you all might have heard about vision transformers, right? Vision transformers?
Yes.
And transformers is actually a Gen AI model. Okay. And it is actually outperforming most of the what CNN architectures these days. So my question is, if Gen AI outperforms deep learning, or if deep learning outperforms machine learning, then why do we have these kind of streams? If we have machine learning, why do we have deep learning? If we can do everything with deep learning, then what is the purpose of machine learning? If we have generative AI, then what is the purpose of having a deep learning if a generative AI could answer everything?
There is this quote which says that not one size fits all. So it depends on the problem at hand and the data available, on basis of which we choose which AI model to go for: machine learning, deep learning, or generative AI.
Okay, correct. So these days, what is happening is that if you're having a problem statement, if you're having a problem statement, immediately everyone is going towards AI. Okay, so the first and foremost role in AI is if there is a problem statement, first thing is that we have to check whether the problem could be solved without AI or not. Okay, if the problem statement that you're trying to address could be solved without AI, then we should actually what prefer to go with that. Okay, never go for what creating an AI model or machine learning model just because it is actually very lucrative these days. Okay, so that is the first and foremost role in the field of AI. Now, second thing, when we talk about machine learning or the significance of deep learning, machine learning, generative AI over others. Okay, so we can say like what each of these things, machine learning, deep learning, generative AI, everything has its own purpose. Like it was said earlier, like generative AI, like I don't know how many of you have tried out using a generative AI model. I'm not talking about ChatGPT. Is there anyone who has used a model like Llama or GPT for that matter? Anyone? Have you ever tried out using a Llama model or GPT model? Okay, the size of these models are so high that suppose if we want to run a machine learning model on a edge device, like on an embedded board, okay, if we want to run this kind of model on an embedded board, we are having some kind of limitations when we consider using a generative AI model, because the size of the generative AI models are so high that we need to do several kind of optimization to these models so that it could be deployed on a embedded board. Okay, so we can say that still, even though generative AI is ruling the industry these days, still machine learning and deep learning has its own significance. It is like suppose if you want to stitch a button, we'll be using the needle. We won't be using knife for that. Knife would be used for cutting purposes, and needle would be used for stitching purposes, right? So everything has its own purposes. Now, some of the basic differences or the difference in the data that we use in this machine learning or deep learning, it could be said like generally most of the machine learning problems we would be using structured data. Okay, structured data. And for the deep learning, we would be using unstructured data. I hope everyone knows what is structured data and unstructured data, right? Can anyone tell me an example of structured data? Structured data. Anyone?
Sir, structured data means row or column or tabular form data, or
Yes, correct.
unstructured means video or video, then images. This unstructured data.
Yes, correct. So structured data like that you see in your Excel, CSV, or SQL tables and all. And when it comes to unstructured data, it's like your audio, video, and images. Okay, so images. Okay, so basic, we can say that generally in machine learning we would be using structured data, and in deep learning actually what we would be using unstructured data. Okay, and when it comes to machine learning, I hope everyone is aware that there is actually three kinds of learning. One is supervised learning.
Unsupervised.
Yeah, correct. Yeah, supervised. Then you have unsupervised. What's the third one?
Reinforcement.
Reinforcement learning. Okay.
Semi-supervised.
Semi-supervised.
Yeah, if you're considering reinforced learning, then I should say that there is four. Okay, then yeah, the semi-supervised. Can anyone tell what is semi-supervised? What is semi-supervised?
It's combination of supervised and unsupervised.
Yeah, what is
Part of
actually
the
happening?
data is labeled data and part of the data is unlabeled data.
Okay, okay, correct. It's like in semi, so I hope everyone is familiar that in supervised learning we are using labeled data,
Labeled data.
and in unsupervised we are using
Unlabeled.
unlabeled data.
Unlabeled data.
And in reinforcement, actually, what we are doing,
Environment.
we are
It is
actually
based on
exposing.
reward and punishment.
Yeah, reward and punishment kind of learning, correct. And in semi-supervised, what is happening is that we are using a large amount of label data. Okay, a large amount of labeled data, and we are using some unlabeled data. Okay, we're using some unlabeled data. So that is what is happening in unsupervised learning. Okay, now, so we can say what, like you are saying, like deep learning was a subset of machine learning, right? In the same way, we can say that generative AI is actually a subset of deep learning. Okay, so in generative AI also what we use is artificial neural networks. Okay, and okay, we use the artificial neural network, and it can what? It can process both the label data, unlabeled data, unlabeled data, using what? Using all the techniques that we discussed above, using supervised, unsupervised, and semi-supervised mechanisms. Okay, so generative AI could be said as what? It is a subset of deep learning, wherein it uses artificial neural networks and it can process both labeled and unlabeled data using supervised, unsupervised, and semi-supervised learning mechanisms. Clear up to this? I hope we are good.
Sir, sir, in the structured data we have taken the text, but in even unstructured data also we have a textual data like in the form of emails and
text
documents and articles like that.
Text,
Unstructured data.
yeah, text basically comes under unstructured data. Like it depends on the volume of it. Okay, suppose I think there were several scenarios wherein if the text is actually limited, then it could be what considered as structured data. But when it comes to a huge chunk of text, then we can consider it as a unstructured data. Okay, it depends on the volume of data that we have. Okay.
Yeah.
Okay. Now, so I was saying generative AI is actually a subset of deep learning. Okay. So basically we can say that deep learning is actually divided into two. Okay. Discriminative and generative. Okay. Deep learning is basically divided into two, which is discriminative and generative. Okay. So what is a discriminative deep learning model? Discriminative deep learning models are the models that you have seen so far. Like it is actually used to predict or classify data. Okay. Used to predict or classify the data. Okay. And discriminative models are trained on data set of labeled data. Okay. Trained on data sets of labeled data. Okay. And what does this discriminative models do? This discriminative model, it learns the relationship. Okay. It learns a relationship between the data instances, and the labels. Okay. It learns a relationship between the data instances and the labels. And once a discriminative model is trained, okay, once a discriminative model trained, then it can be used only to predict new labels for the data instances. Okay, like I hope you all might have, I don't know whether it has been trained. I hope some uh, classification, image classification problems were discussed, or was it?
Yes.
Yes. Like, oh, could you please tell me what was that problem? To classify what?
So the data set was taken for cats and dogs and to identify whether it is a cat or a dog.
Yes, correct. Okay. So what is actually happening over there? The data set is actually data set contains only two categories like cats and dogs, and whatever model that you're training is using this data set can only be used to what? Used to classify whether the given image is that of a cat or a dog. Okay. So that kind of models is what we call as discriminative.
Binary classification.
Yes, binary classification. In general, we are saying that discriminative model. Okay. So here actually we are having two classes. That is why we are calling it as binary classification problem. But in general, we call these kind of models because it serves only the purpose of the data it is fed.
So once again,
Okay,
when the discriminative, once again, please.
so discriminative models basically means what? With whatever data we are training a model, the model would be able to answer only to that data. Okay, only to that kind of data. Okay, suppose if we are training a model using the images of cats and dogs, that model could respond to only what? Cats and dogs images. Okay, it is actually, it doesn't know if we give a new image, it may not be able to perform well. Okay, so the knowledge of the discriminative models is actually limited to the data. Okay, limited to the data used for training the model. Okay, used for training the model. That such kind of models is what we call as discriminative models. But when it comes to generative, we can again say discriminative. This could be said as a very what core point. Like discriminative models, it predicts new labels for the data instances. Okay, like for example, if you're having a image, if you're having a image of a flower, discriminative models would be able to say like, okay, this is a image of a flower. Okay, this is a flower. Okay, means it is able to predict the new label for the data instance. Okay, this is the data instance and it is actually able to predict the label flower. Okay, but when it comes to generative models, When it comes to generative models basically new data instances are generated. Okay, new data instances are generated. So earlier in discriminative model, we are actually able to predict only the new labels based on the data instances that was used for training. But when it comes to generative models, we are able to generate new data instances. Like for example, we are actually giving a image of a flower, okay, and it will give us a image of what? Some other flower. Okay. I hope that is clear. Is it clear?
Yes, sir.
Yeah. Okay. So basically, we can say that in discriminative models, okay, discriminative models, we say like discriminative models, what it does is that it learns a conditional probability. Okay. Discriminative model learns the conditional probability of y given x. Okay. Discriminative models learns the conditional probability of an output for a input. Okay. But when it comes to generative models learns the joint probability distribution. Okay. Joint probability distribution of what? Of our input and our output. Okay. And then it predicts what? Then it predicts a conditional probability. Then it predicts a conditional probability. Okay. Is it clear? So in discriminative model, basically conditional probability of our output given an input is being learned. Whereas when it comes to generative models, a joint probability distribution of input and output is learned. And based on that learning, conditional probability is being predicted. Is it clear?
Yes.
Yes.
Okay. We can always say it with a diagram also, like when it comes to what discriminative model, we'll have a data. Okay, we'll have data and we'll have labels. Okay, and both these things will be actually what going to give it to a predictive model. Okay, a predictive model, and the model will predict what? Labels. Okay, so basically the output is what? Output is labels. Okay, but when it comes to generative model, we are actually giving some what? Unstructured data, and it is actually given to what? Generative AI models. And what it does, it learns the patterns. It learns the patterns of the data that is given, and based on that learning, it is actually what? Generating new data instances, not labels, new data instances. Okay, I hope that is clear. Is it clear?
Yes, yes.
Okay, we can say that generative AI, there are actually so many concepts that is actually powering this generative AI. Some of it is like auto encoders, then you have transformers, then you have GANs. So these are some of the things that is actually powering the generative AI. I hope at least some of you might have heard about autoencoders, transformers, and GANs. Am I right? Yes or no? Autoencoders, transformers, GANs. Okay, so what is autoencoder? Anyone having any idea on what is an autoencoder or how does it work? Or anyone has any idea like how generative AI works, like how this chat GPT is actually giving us an output when we are getting a prompt, or how models like DALI is actually giving us an image when we are giving a text input? Having an idea on that?
Realistic images.
I couldn't get that. I couldn't get that. Could you please repeat?
Realistic images, sir.
Based on?
Realistic images.
Yeah, realistic images. How is it being generated?
Y'all
Y'all might have seen several what Instagram reels wherein you can see some of the famous songs in some of the famous songs of the country is being converted to the voice of our prime minister, or you would have seen some of the videos that is being generated using AI and all. So how is these things happening? We know that generative AI is working behind that. What is the core thing happening behind? So we can say that the core functioning happening behind is with the help of this autoencoders, transformers, and GANs. Okay, so what is an autoencoder basically?
Generate the text and
Autoencoder could be basically said as what? It is actually a unsupervised learning mechanism. Okay, autoencoders are a unsupervised learning mechanism. Okay, learning mechanism. So basically, autoencoders have two parts. One is encoder, and second is decoder. Okay, and what does this encoder do? This encoder, it takes the input. Okay, it takes the input. Suppose the input is that of a flower. Okay, okay, this is the input. Okay, it takes the input and it learns how efficiently this image could be compressed. Okay, how efficiently this image could be compressed and encoded. Okay, and encoded. So when we are giving when we are giving an image as an input to autoencoder, the first part, that is the encoder, what does the encoder do? Encoder will identify like how efficiently this image could be compressed and encoded. Okay, so this encoded result of this image is actually stored in an area which is called as latent space. Okay, latent space, like visually we can just say it like, suppose this is latent space. Okay, it is actually a very high dimensional space. Okay, suppose if this is latent space. Okay, and suppose if you are giving a image of a tree. Okay, you're giving a image of a tree. I'm very sorry with my drawing. Okay, you're giving this tree image as an input to the encoder. Okay, and what does the encoder do? Encoder will compress this image. Compress this image. How it compresses the image? It actually compresses this image efficiently. How does it do efficiently? What does it mean efficiently? It has to consider various attributes. The encoder has to consider various attributes that says that this image is a tree. Okay, that says that this image is a tree. What could be the attributes? It could be the length of the wood, the stem, the number of leaves, those kind of things. Okay, so uh, I'm hearing some background noises. Could you please, could everyone please be mute? You're mute, please. Okay, thank you. Okay, so basically what it does, this encoder identifies all the attributes that defines this image as a tree, and it what encodes it into a latent space. Okay, latent space. Now this is our latent space, and in this latent space the tree image is coming in this area. Okay, now if I'm going to give another tree's image, and it looks like somewhat this pine tree. Okay, still this again is a image of a tree. Okay, it will be actually what it also would be what encoded and stored in the latent space as a different data point. Okay, now suppose if I give a image of a what car. Okay, if I give an image of the car, this image also would be what it also would be compressed, and it also would be encoded and stored in the latent space in a very different position. Okay, it could be in this position. Okay, so that is what encoder is doing. Encoder basically what it is doing, it is taking the input and it is efficiently compressing that input and is storing that input in a latent space in a encoded format. Okay, that is what encoder is doing. Now what is a decoder doing? Decoder, it actually learns how to reconstruct this labels. Okay, whatever data points that we have in that latent space, whatever data points that we have in the latent space, decoder learns how to reconstruct it, into the image or into the data point. Okay, into our input data point. So basically in autoencoder, what is happening? We are giving a input to the autoencoder. The encoder will take the input, it will compress the input, and it will encode the input, and after encoding it will be stored in a latent space. And decoder, what does the decoder do? Decoder takes this what encoded value, decoder takes this encoded value from the latent space and learns to reconstruct it into the what initial data point. Okay, like another example we can say that suppose if we have a image like 8. Okay, we are having an image of handwritten digit 8. So this is the input, and we are going to what encode it. We're going to encode it, and once we encode it, the encoded output, the encoder output would be looking somewhat like this. Means it is actually trying to identify, it is actually trying to capture only those key parameters of this image. Okay, those key parameters of this image that is needed to define this image as a number 8. Okay, so for defining this number as 8, we don't actually want to have this entire data. Now the advantage here is, like suppose if this is a what 25 cross 25 image, it could be what brought down to like a 6 cross 6 matrix. Okay, so there is a what reduction in the size of the data. Okay, and from this actually what we are going to do, what the decoder does, the decoder reconstructs the image, now at least some of you might be having this question like, what is the advantage of this? Like we are having an image, we are actually compressing it, then we are decompressing it. What is the actual use of it? Can anyone take a use? Can anyone get what is the advantage of this thing, autoencoder?
Sir, the data can be easily transmitted. So much of data, sir. By seeing this
Yes,
one,
correct.
we are concluding that it is very small amount. But the data what we are going to transmit will be very huge if you are compressing that and then you are going to expanding the decoding it, sir. Am I right, sir?
Exactly.
Reducing number of pixels, particular
yes,
part
correct.
of image.
Yes, correct. Exactly.
Then we
like,
can easily transmit with less intensity of the image.
It's not a matter of transmitting actually.
Transmitting, that is in terms of information.
No, it's actually not a matter of transmitting. I don't know how many of you have trained a AI model. I hope at least some of you might have an exposure to training a AI model, right? So for training an AI model, it usually takes so much of time. Now suppose if you're having these kind of very big images in your hand, it takes so much time for training. Okay. Now suppose if you are building some generative AI models, if you want to build a generative AI models. I hope at least some of you might be aware that what billions of amount is actually invested on generative AI models. I think today there was a news that what the fire that has happened in Los Angeles. This what very interestingly they are connecting it to Chat GPT. Like it is actually because of all this what generative AI models or development of the generative AI models is what causing it's what causing this what climate change and those kind of things. Okay, so much kind of what energy is being wasted or not wasted, so much kind of energy is being used in this for training a generative AI models. And so when it comes to using these billions of data, definitely we want to compress data in such a way that it should have only the useful information and all the noisy information should be what taken away from the data. Okay, that is what autoencoder is doing. Okay, that is what autoencoder is doing. Okay, so I hope autoencoder is clear for everyone. Now let's move to
Sir,
transformers.
sir,
Yeah, please.
sir, sorry for disturb us. Sir, so this example is not clearly understand. Getting
Okay,
some
just a
point,
second.
but
Sir,
Okay, just a
whenever
second.
we
Just a second.
are, sir, whenever we are commanding to the tools like GPT that I want this kind of image, so is it collecting all the images from the latent space and is giving the picture
Yes,
like that?
yes. Yes, I'll do one thing. I'll just get to that, like how we are actually how this kind of big models are being trained. I'll just get to that. Before that, let me just show working of autoencoders. I believe I have a notebook on that. Where is it? Autoencoder. Autoencoders. Yeah, this one. Just a second. I'll just quickly show like how an autoencoder works. Not this one, I'm sorry. It is autoencoder simple. So at least some of you might be familiar with this data set which is called as MNIST, that is actually available on Colab. I hope everyone is familiar with Colab. Okay. So I'm not going to execute the code right now. This is something that I've already executed. So we are having a data set which is called MNIST, which is actually images of handwritten digits, like you can see 0 here. Okay, and what we are doing is that we are actually going to create a autoencoder. Okay, we are creating a encoder. Okay, we are actually passing our images through encoder, and we are taking it through what decoder. Okay, we are passing the image through encoder and passing and taking it through decoder. And once we completely build this model, once we train this model, and when I'm passing an image, you can see that this is actually a representation. Okay, this is actually a representation of a data. Okay, this is actually a encoded representation of a data in this. Okay, like we are having an image, of a handwritten digit. Okay, and this is the encoder representation of that image. You can see that this encoder representation, the size is 7 by 7. Okay, you can see it's 7 by 7. Okay, it takes only 49 pixels to represent that data. It takes only 49 pixels to represent that data. But in fact, the original data is this one. This is the original data. Okay, the image was of handwritten digit 7. Okay, and on encoding this image, it is actually represented as this matrix that you're seeing here, which is a 7 by 7 matrix. So this image, which was actually a 25 cross 25 image, means like it takes around 625 pixels to showcase this image. And this 625 pixels is actually what brought down to 49 pixels. Okay. Now, this is actually the encoded value of this image. Okay, this is the encoded, this one is the encoded representation of the number 7. Okay, now if we pass this encoder representation to a decoder, okay, it is actually, we are passing this encoded output. This is the encoded output. This encoded output is actually passed through a decoder, and you can see that decoder is actually giving back that image. Okay, so basically what is happening here? Basically what is happening is that it is actually compressing the size of the image. Okay, it is compressing the size of the image and encoding that image, storing it in a latent space. Okay, and I hope that is clear. Is it clear?
Yes, sir.
Now, why we are doing it, I'll come to that. Okay, why we are doing this, I'll come to that. Okay,
sir,
before coming
sir,
to that,
second, sir. Sorry to
yeah,
interrupt, sir. Where that latent space, where it stores, sir? Can you show me the coding, sir? I have been coding something.
You can actually see it over here. So first of all, actually we are actually, you can see that at this point, actually we are stopping with the encoder. Okay, at this point actually we are stopping with the encoder. Okay, and when we say like latent space, where it is stored, actually how can I describe that? It could be said as like how
Okay,
we
sir,
train the
sir,
model.
understood, sir. I understood,
Yeah, how
sir.
we
Out of the ReLU
it is
function, yes, sir. Yes, sir.
yeah, it is actually a kind of what, when we say that, I hope you might have trained some models, and we say that we are
Yes,
storing the knowledge in some kind of a format, like in the same way.
yes, sir.
Okay,
So once
so
again, sir, again,
For ReLU is activation function, no?
sir.
What?
So ReLU is activation function. So what is latent space, sir?
So again, like latent space is basically, now it could be said as what, it could be a kind of a like, you said that you had trained a model, right? You had trained some what, image classification models, right? Yes or no?
Yes.
During the sessions. Okay, so this model actually, it has a kind of knowledge stored, right? Whatever model that you're training for cats and dogs, you train the model, and after that you say this model as some kind of what, TensorFlow or
Pattern.
Python, yeah, kind of thing. In that, it could be said, this could be also said as in the same way. It is actually a kind of a knowledge base that we are creating. Okay.
We call database.
What?
We call
So
database.
can we call it as a memory space where compressed versions of the
Exactly.
original images are stored, collection like?
Yeah, we can. Yeah, that could be said as a definite explanation. Yeah, correct. Okay. Now, why we are actually doing this? Okay, why we are actually having to create a latent space, or why we have to use this autoencoders? We'll come to that after discussing about transformers. Now, transformers, I hope that it is actually something that has actually brought a revolution in 2018. Okay, like at least some of you might have a chance to go through the papers of transformers. So what is transformers doing? Transformers is actually what, it transforms something from one sequence to another. Okay, it transforms something from one sequence to another. Okay, now for example, let's take like, we are having an example, like having a sentence like, what is your name? Okay, what is your name? Now, yesterday you have seen recurrent neural networks, LSTM, and there were discussion about GRUs and all. So one of the key things, or one of the major advantages of transformers, is that it addresses the limitations that we had on GRUs or LSTMs or RNN, and that is the sequential input of data. Okay, sequential input of data. Now, suppose if we want to create a translation model, if you want to translate this sentence, what is your name, to Hindi. Okay, so generally in RNN or LSTM, what it does is that it actually takes word by word. Okay, it actually takes word by word and then tries to what, translate it. Okay, now if we translate this this sentence into Hindi, okay, we translate this sentence into Hindi, it actually the question changes, the sequence or the order of the words is not in the same way how we see it in English. Am I correct or wrong?
Yes, sir.
Yeah, correct. Like in English, it is what is your name. When it comes to Hindi, आपका नाम क्या है? Okay, so if we go for a sequential kind of translation, that won't actually help us over here, and that is where transformer actually comes into play. Okay, now in transformer again, it also has what? It also has a encoder and a decoder. Okay, transformer also has an encoder and decoder. Now the encoder in transformer, it actually takes the input. Okay, it takes the input and provides the encoding. Okay, and provides the encoding of the part of the sentence or part of the sequence that is relevant to each other. Okay, encoding, it takes the input and it gives us the encoding, the part of the sequence that is relevant to each other. Okay, that is relevant to each other. Okay, now what does a decoder do? Decoder again takes this encoding and uses it takes this encoding, whatever encoding that is generated from the encoder, it takes the encoding and uses the context. Okay, uses the context that is derived from the encoding. Okay, uses the context derived from the encoding, and using that context, it generates new text. Generates new text or new sequences. New sequences. Okay, so that is what the encoder and decoder in transformers do. Now, basically, we can say that transformers is actually a kind of semi-supervised learning model. Okay, we would be having the pre-training of these transformers. Okay, pre-training. The pre-training of transformers is happening using unlabeled data or unsupervised learning. Pre-training is happening using unsupervised learning, and fine-tuning of the model. Fine-tuning of the model. Fine-tuning of the model is happening using supervised learning. Okay. So basically, we can say that transformers actually don't process the data in a sequence or in an order. Okay. Transformers actually they process the data in a parallel way. Okay. Transformers process the data in a parallel way, in a parallel manner. Whereas our RNN or LSTM for that matter, it actually takes the data in a sequential way. Okay, so transformers they process the data in a parallel manner, and for this they actually use a mechanism which is called as attention mechanism. Attention mechanism. Okay, now what is this attention mechanism doing? Attention mechanism basically what it provides the context. Okay, it provides the context around the items in the input sequence. If this is the input sequence, what is the context around this input item? What is the context? So attention helps in extracting the context of the input sequence, and that is what transformers doing. I hope that is clear. Is it clear?
Yes, sir.
Yeah. Now let's move to how generative AI models are trained or how generative AI models are working. Okay. Now when it comes to generative AI, this is generative AI models. Okay. So generative AI models, it actually first of all, it takes a input. Okay. And this input, it could be what? It could be text, it could be audio, it could be video, anything. Okay, it takes the input and using autoencoders. Okay, using autoencoders, what does it do? It compresses the data. Okay, it compresses the data and maps the meaningful features. Okay, map the meaningful features into a latent space. Okay, latent space. Okay, so first of all, it takes the input. It could be text, audio, video, anything. This input is passed to autoencoders. Okay, and this autoencoders, what does it do? It compresses the data and encodes the data. So encoding happens in such a way that it will keep only those important attributes or important features that describes this input. Okay, that describes all the other what attributes or features would be neglected. Only the important features and the important attributes, it will be what taken and it will be mapped in a latent space. Okay, and this mapping, this latent space is then given to transformers. Okay, this is given to transformers. Now what does a transformers do? Transformers, it actually identifies the complex dependencies between the elements. Okay, it identifies the complex dependencies or relationships. Okay, dependencies or relationships between these elements. Like I said, we'll be having a suppose if we have a image of a flower. Okay, it is first given to autoencoder and it will what map this in a latent space. This is the latent space. You'll map it over here somewhere. Okay, and this latent space is then given to transformers. And what does the transformer do? The transformer would what identify the, suppose we'll be having not only one image, we'll be having so many images of flowers, and we'll be having so many images of flowers. Oh, okay, just a second, I'm just getting a call. 1 minute. Yeah, sorry, I'm back. Okay, so we'll be having so many images of flower, and it will be what? It will be actually mapped in this latent space, and this latent space is then given to transformers. Okay, transformers, and the transformers, what it'll identify the dependencies or relationship between each of these elements. Okay, once it identifies this, this transformers, what it'll do? It'll generate, after identifying the dependencies and relationship, it generates new data. Okay, it generate new data based on the learnings, based on whatever learning it has done over here, based on whatever identification it has done over in this area, it generates new data. And this new data that is generated, it will be also in a latent space. It will be also in a latent space. And from this latent space, we'll again use autoencoders decoder and get back the refined data. Get back the refined data. So this is how basically a generative AI model is working. Like we have a input, and that input would be what? It would be converted into latent space using autoencoders, and that whatever values, whatever data points that we have in the latent space, it is passed to transformers. Transformers identifies the relationship. Okay, transformers identify the relationship between uh, various elements in the latent space, and based on that identification it done, it will generate new data. It will generate new data, and this generated new data, it will be in latent space, and this latent space, from this latent space, we'll use autoencoders decoder and make it back to a refined data. Okay, that is how basically a generative AI model works. I hope that is clear.
Sir, can you take another example for this working of this diagram?
Working of this diagram. Okay, let me just think. Suppose, how can we say? Okay, suppose you, like I said, okay, suppose you have a kind of what? I hope that image example is not clear, right? Then I'll just think of something else. Just a second. I just need to get a clear analogy that would help over here. What could be done? What could be done? Okay, suppose we can say that we can say that some suppose you are having an image. Okay, you want to actually what? I hope at least some of you might have some of you might be familiar with this thing called stable diffusion, right? So I'll just tell how stable diffusion works. Okay, so it is actually working on this same principle. Like it takes an image. Okay, it takes an image and it compresses this image. Okay, like for example, this image of a flower. Okay, it compresses the image. Not only one image, I'm saying when we say it takes an input data, this input data, it is actually a billion of pictures of flowers, various flowers. Okay, and this is actually compressed, and whatever data that is, or whatever attributes that is defining this flowers, it is actually stored in a latent space. Okay, this is latent space. Okay, and from this latent space, from this data latent space, our transformers, it will learn to modify. Okay, it will learn to modify or generate, learn to modify this latent space or generate new latent spaces. Okay, or generate new latencies. Okay, and based on that study, it will generate what? After generating new latent spaces, what? The same encoder, same autoencoder that we have used for compressing, we'll use the same autoencoder, and this time we'll be using the decoder portion of the autoencoder. Okay, decoder portion of the autoencoder, and this decoder portion is applied to the latent space that is generated. Okay, and from which actually we'll be getting a refined output. Means like we'll be getting what? Different images of flowers based on use cases. Suppose if you want to generate new flowers, it will give you new images, or it will give some kind of text descriptions. I hope that is clear. Or do you want me to
Yes,
give?
sir. Yes, clearly getting points, sir. Absolutely.
Yeah. So that was with this generative AI thing. There are some other things also needs to be discussed, like the problems that we face with generative AI, which is kind of things like hallucination and all, which I believe right now we have come to an end of the time, which I hope tomorrow also we are having a session from 2 to 3 in the afternoon. So we'll be discussing those kind of things in that session. So far, if anyone is having any question, please feel free.
May I have your
Yeah,
mail ID,
definitely.
sir?
I'll
That is
definitely share
shared
that.
in Narayanaguru Siddhartha College of Engineering, and I am following you to LinkedIn, sir, and I am from Tamil Nadu, sir.
Oh, okay.
We'll meet there, sir.
Okay.
Thank you.
So,
Yes, sir.
so if you're having any kind of questions, please feel free to ask. I think
Lot of questions,
the
doubts are there,
next
sir.
week.
But you
Okay.
clearly explained and you patiently explained. And once again, I thank the organizers letting me inside this FDP. And again, I'm thankful to you, sir. Really, sir. Awesome explanation. And tomorrow also we'll be having the same talk by 2:30, and the schedule has been shared last like that. And I will meet there, sir. And allow me in LinkedIn. Thank you, sir.
Sure, sure, sure. So if you're having any kind of questions, please feel free to note it down at least today, because I think the next speaker is already in for the meeting, and I have my work time starting from now. Okay, so I have to leave. Okay, so please note down your questions or doubts that you have. We'll discuss tomorrow in the meeting. Okay.
Okay.
Thank you very much.
Thank you, sir. Very nice experience session is there, sir.
Thank you. Thank
you. Namita?
As we come to the end of today's enlightening session on recent advancements in generative AI, we have gained valuable insights into this rapidly evolving field. Mr. Abhimanyu KS has expertly guided us through the latest trends, challenges, and opportunities in generative models. We have learned about the groundbreaking techniques driving innovation in AI and how these advancements are reshaping industries and academia alike. We extend our heartfelt gratitude to Mr. Abhimanyu, Senior Engineer in Data Science and AI at Walmart, for sharing your valuable expertise and experiences with us today. It was truly enlightening to hear about the initiative work you are contributing to at Walmart, which has sparked new ideas and inspired us to explore the exciting possibilities of generative AI further. We eagerly look forward for your next session tomorrow. To all participants, I would like to extend my deepest gratitude for your active participation throughout this session. Your enthusiasm and engagement have been truly appreciated.
Now we are moving to the next session.
Once again, a hearty good evening to all. I'm Ron Thomas Roy, scholar at SJCET PALAI, and it's truly a privilege to be part of today's session. An investment in knowledge always pays the best interest. I quote Benjamin Franklin. Ladies and gentlemen, as we begin the next session for the day, I welcome Assistant Professor Jacob Thomas from the Department of Artificial Intelligence and Data Science, who is chairing today's session. His guidance and expertise plays a vital role in ensuring the success of today's program. Thank you for being with us, sir. It is my privilege to invite Professor Jacob to commence the next session and to introduce our speaker. Over to you, sir.
Thank you, Ron, for the invitation. Now, ladies and gentlemen, it is with immense honor and excitement that I welcome an extraordinary guest to our event. With an astounding 38 years of experience in the ever-evolving field of computer science, our next speaker is nothing short of a luminary. Dr. Larry Binbaum is a professor of computer science at Northwestern University, Illinois, and a visiting professor of artificial intelligence and data science at the Geo Institute. He is also the co-director of the Intelligent Information Laboratory, where his innovative research keeps pushing the limits of human interaction and artificial intelligence. Dr. Binbaum's journey began with a PhD in computer science from Yale University and has since emerged as a leading innovator. His co-founding of Narrative Science, a revolutionary venture that transforms complex data into human-like narratives, is a testament to his ability to bring cutting-edge technology to life. This innovation has transformed industries, making AI more accessible and impactful. Throughout his impressive career, he has made significant contributions to fields like intelligent user interfaces, natural language processing, and human-computer interaction. Additionally, his leadership has expanded to projects at the Medill School of Journalism and collaborations at the intersection of AI, media, and education, shaping the future of technology and its societal impact. Dr. Larry Binbaum's career also highlights his pivotal contributions as a co-founder and chief scientific advisor at Allovoice INC, a platform that democratized citizen journalism by enabling users to share and report on events worldwide. This initiative showcases his commitment to empowering individuals through technology while advancing innovative applications of AI in media and communication. His efforts have garnered international acclaim, and his enthusiasm for expanding the realm of artificial intelligence capabilities is incredibly motivating. Intelligent interactions on the multiple AI substrates is the topic that we have the honor of hearing from Dr. Binbaum today. His insights and expertise promise to leave us enlightened and energized about the possibilities of the future. Over to you, Dr. Binbaum.
Hello. Well, thank you, Professor Jacobs, for that kind introduction, and Dr. Thomas for inviting me. And I also want to thank Professor Lakshmi G, formerly of St. Joseph College and now at St. Thomas College, for brokering that invitation. I appreciate it very much, and I'm happy to be here today from Chicago to talk with you about building natural interactions, intelligent interactions on top of multiple AI substrates. But first, I want to make sure people can hear me.
Yes,
Yes,
sir.
sir. Good morning.
Okay, perfect. Thank you so much. Let's see if I can actually share content, screen window, or tab. Good grief. Sure. Hold on just a second. Oh, good grief. Okay, so I hope that this will all work, and I will be able to okay. I don't want to share. Let's see what I want to share. I apologize. I need some help here to. Okay, this is what I want to. This is what I want to do. Okay, good. Give me a second here to. Let's do this. Can you see my screen now?
No, sir.
All righty. So I think we're ready to go. Okay, can everybody see my slide?
So I don't think it's visible.
No, the slide is not visible?
No.
What are you just seeing? My face?
Yeah. Yeah, only you, not the slide.
All right, let's do this then. Let's try something. And I apologize. I normally use Zoom, and so apologies for this kind of fumbling here. Let's try this again.
No, it's all right, sir. Take your time.
Yeah. Let's see if I can. Okay, let's share a window. No, let's share the entire screen. Okay. Okay, can you see this the slide now?
I'm afraid not, sir.
Yeah, my usual. I apologize for this fumbling. It's embarrassing, but what can I do? Let me see if I can. Fine, let's do this here. Can you see the slide now? Yes or no?
No, sir. No.
Okay, so someone needs to.
Sir, can you rejoin? At that time, it
Should
will
I
be okay, maybe.
Okay, I'll rejoin. Okay, sorry about this. Let's try that again then. Okay. Well, I just don't understand why. I mean, I'm sharing the entire screen. Okay, I want to share my entire screen. Okay, so I see. To share audio, share a tab instead. I don't understand. All right, I'm sharing a window. You need permission. Okay, I'm sorry here. Security and privacy. Oh, good grief. Okay, maybe this will help. Camera, microphone. Alrighty. Can anybody help me here as to what I need to set for my permission to allow Teams to use this to see my screen?
So I guess you can go forward. Just click yes.
Click where?
Just grant permission to share your screen.
So I just say reset permissions here? But I mean, what do I say permission on?
I guess when you press share first, it asks for two options: the screen
All right,
and the
so
window.
I'll try that again then. Okay.
Yeah.
Okay, good. Thank you. Let's try that one more time. No, it didn't ask for my permissions this time. I'm going to rejoin, okay? Sorry about this.
No, it's okay, sir. Dear participants, we'll just wait for a few minutes till he rejoins, and then we can continue with the session.
Can you hear me?
Yes, sir.
Okay. Let's try this. Okay. All right, I'm gonna have to try this again, unfortunately. Hello there.
Now
Can you hear
it's
me now?
now it's ready.
Okay, thank you very much. I apologize for that faux pas, and thank you for your patience while I work through all this stuff. And as I said, I normally use Zoom, so not as used to Microsoft Teams as I ought to be. Thank you again for your patience, and again thank you for the kind introduction and the invitation to join this today. I've spoken at AICTE events before, and I appreciate the opportunity as always. Let's start the show. So today I'm going to be talking to you about building intelligent interaction on multiple AI substrates. I would welcome questions during the talk, but it might be difficult for me to, I'm not going to be monitoring the chat or anything. So if anybody would like to enter a question, perhaps the moderator can interrupt me and call that out, or we can wait until the end for these conversations to happen. And as was mentioned, I'm at Northwestern University, which is in Evanston, Illinois, just outside of Chicago, and also at Geo Institute in Navi Mumbai. So natural interaction is communication between people and machines that is as fluent, interactive, and productive as interaction between people. And the paradigmatic model for this, of course, is conversational interaction between two people or multiple people. But the interaction does not need to be in natural language to be natural or fluid. It's important for many reasons to have this kind of interaction between people and machines, but two of them stand out. And the two themes I'm going to talk about today in the context of this whole thing are the idea of natural interaction, and second, the idea of picking the right tool for the task. So let's start with natural interaction. As I mentioned, this is a common, perhaps you've seen this example before, but here we have an image, and we ask you, what is this? And you might say, well, I see some colored hash on the screen. And we ask a computer vision system trained as a visual classifier, and it says that this is a robin. And perhaps we can detect a little bit of redness somewhere there in the middle, but it certainly doesn't look like a robin or even a bird in any way to us. Okay? Or we might ask, what do we think this is? And of course, you and I see a stop sign, but because of the cleverly placed little stickers on the stop sign, the computer reads this as speed limit 45. So what are we to make of this? Well, what we're to make of this is that AI systems don't work the way people do. They make different mistakes, and the different mistakes they make are so different from the mistakes that we would make that it's clear that they're not looking at the world in the same way that we're looking at the world. And therefore, they have different strengths and weaknesses. And so the most exciting prospect that this opens is the prospect of collaborative human and artificial intelligence, the idea that we can build systems that enable people and machines working together to do things that neither could do on their own. This is the other reason, by the way. So the standard modality that most of us use to interact with today is our cell phone. And our cell phone is an amazing mechanism, but what's not good on the cell phone is the standard graphical user interface, or GUI, as we've come to know it and love it on laptops and desktop computers, with using a mouse or a touchpad, where we can do clicking and dragging and dropping and use menus and so on. All of those incredible techniques and technology don't really work on a cell phone because there isn't enough screen real estate, and our finger as a pointing device is not really accurate enough given the size of the screen. And for these reasons, conversational interaction seems like the most obvious thing to do, or some kind of natural interaction. Now, my other theme this evening will be on picking the right tool for the task. So the course that you're undertaking right now is primarily a course in generative AI, which is perhaps the most powerful of and certainly the most recent revolution in AI. But there are actually a lot of AI technologies to choose from in building an application. And generative AI isn't always the right tool for the job. And I'm going to give you an example of that. Let's consider information extraction. Information extraction is the task of looking at unstructured data, typically textual data, and then pulling out structured data from that to enter into a database of some kind. So a very standard task, and one of the standard versions of this task is to look at EMRs, or electronic medical record systems, and pull out information from doctors' notes that have been entered into these systems. For example, prescriptions that have been written by doctors. Now, a number of years ago, I saw a talk by an amazing young scholar from a very famous engineering school in the United States that is normally known by its the three letters that signify the name of the school. And the candidate, this young scholar, was talking about the use of large language models, generative AI systems, to extract these written prescriptions. Now, it turns out that LLMs, and she talked about a number of interesting advances that she'd made to make them do this job, but still the error rate was pretty high, maybe 10, 15% error rates in the extraction. And the errors it made were kind of interesting. Like, for example, two kinds of errors. One is that it would often assume that a drug had been prescribed if it had read earlier in the record that that the patient had been diagnosed with a certain illness, because that medicine would often be prescribed for that illness, even though in this instance it had not been prescribed. So it would make up that the drug had been prescribed because it usually was. And the other problem it had is that when new drugs were introduced into the pharmacy, since it hadn't seen any text that included this new drug name, it had a hard time actually extracting the drug name in those instances. So there's a much older technology for information extraction using what's called regular expressions. And many of you may perhaps know about regular expressions. It doesn't really matter what they are, but suffice it to say they're very simple grammatical structures for representing phrasal patterns in English or other natural languages. And a lot of information extraction systems have been built using regular expressions. In this instance, actually, to be perfectly candid, I think regular expressions would have been the right tool for the job. They're much simpler, computationally simpler than LLMs, first of all. They wouldn't make up that a doctor had prescribed a medicine just because a person had been diagnosed with an illness for which that medicine was typically prescribed. And the minute a new drug was entered into the pharmacy, a regular expression could actually use that because it could be immediately updated from the database in which the pharmacy was the list of drugs to be prescribed was actually there. So that's a case really of where generative AI might not have been the right tool for the job. So I'm going to talk about four kinds of tools today. The first being standard information retrieval. And I'm going to talk a lot about how to build intelligent information systems using standard information retrieval. The second set of tools will be text analytics, which will be very standard machine learning systems, classifiers of various kinds. And there I'm going to talk about the work I've done in computational journalism using these kinds of tools. The third kind of applications I'm going to talk about will be data storytelling systems. And here I'm going to be talking about very specialized or bespoke inference models and how they play a role here. And then finally, I will talk about LLMs and neural language models in the context of conversational interaction and the work that I'm currently doing with my students in that space. So let's start with intelligent information systems. Here again, we're going to be building on top of bog standard information retrieval using TF-IDF, something like that, as the substrate. So this is the eye of the needle. You will all recognize this. Any questions so far, by the way? Are we good?
Yes, sir.
Okay, good. So this is a search box, as you recognize, and I call this the eye of the needle because it's easier for a rich man to get into heaven than it is for you to get all of the thoughts out of your head through this tiny little text box and out into the internet, and then get back some answers from that. And absolutely amazing that it works, because typically you will enter one word or maybe two or three words into this text box, and yet you'll still often get back something that's very useful for you. And that's actually another story, and actually a complicated story. Really, the reason why it works is because usually you want the same thing that everybody else wants. And so, and this is where things like PageRank come in that actually make it possible to find the most popular things and return those to you. And that's why it typically works. We were actually interested in, and I'm talking about my colleague Chris Hammond and our student Jay Budzig. We were very interested in the idea of, could we automatically formulate these queries rather than asking you to formulate them? In other words, instead of having you try to get the thoughts out of your head into that little narrow text box, could we automatically understand what information you needed by looking at what you were doing online? And our first solution was a system called Watson. And from Watson, I learned a number of things. But the first thing I learned from Watson is to never call a program something that a much more influential and important program will be called later in time. This has nothing to do with IBM's famous Watson, too bad. And in fact, actually, it's named after a different Watson altogether. But again, that's another story for another time. Here, the user is writing a PowerPoint presentation, perhaps for a class, on jazz and the American culture. And as our user is writing this PowerPoint presentation, on the right, you see a set of suggestions from Watson of web sites that have information that might be relevant to the user as he or she is writing this, building this PowerPoint deck. In other words, this serves as a kind of automatic research assistant, retrieving things for you that are relevant to what you're trying to do and presenting you with information that will be useful to you in the context of your work, in this instance, the context of writing this PowerPoint presentation. And the way it works is no mystery. It does context analysis, which is really basically keyword analysis. In other words, it finds the words and named entities, in other words, proper nouns that are highly mentioned in the text. It also has some other heuristics, for example, that words that are bolded or words that are in headings or titles are more important, that words that are near the top of a document are typically more important, and so on. So it does this kind of context analysis, figures out the words that it needs to use. And of course, it has to do this in terms of words because the information retrieval system underlying this works in terms of the words or terms that are in the document. So there's no other choice here really as a representation for the document because that's what the backend system is using. It then automatically forms queries using these words that have been extracted. It manages those queries to a variety of information sources, for example, Google or whatever your favorite search engine is, perhaps proprietary search engines or databases even. It filters and ranks the results, and finally it presents them back to you, for example, in a sidebar, as you saw on the previous screen. And this system was fast, it was automatic, and it was better than human. And what I mean by better than human is that if you actually tried to formulate queries yourself, and we did this experiment, or asked Watson to do it for you, and if we mixed up the results that came back from the queries that you had formulated yourself versus the ones that Watson had formulated and presented them to you in a list, you would typically judge that approximately 2/3 of the documents that came back from Watson were relevant to what you were trying to do, whereas only 1/3 of the documents that came back from your own queries were relevant to what you were trying to do. And so Watson was really twice as good in terms of the accuracy of its retrieval. So we were very excited by this, and we actually started a company to manage this process. And the company actually had a reasonable run, and it didn't turn the world on fire. And one of the reasons it didn't actually was as we started to actually use the thing or put the thing into more natural settings, what we found is that people said, yes, this is on point, it's relevant, but it's really not very useful to me because I already know this. You're telling me something I already know. What you're presenting to me is more of the same. And we began to realize that the reason that this had happened is that we were utilizing the standard information retrieval paradigm. And in information retrieval, the similarity between two documents is a proxy for the relevance of one document to the other. In other words, the more similar the documents are, the more relevant they are to each other. But we can see that in the limit, this can't be true because the most relevant document to a document that you already have in your hands is another copy of that document. And that doesn't provide you with any new information at all. So it's immediately clear that what makes a document relevant is that it is similar in certain respects and dissimilar in other respects. And so Watson relied on noise and the size of the internet to achieve the variation that was necessary to provide truly relevant documents. And this raised the question, can we do better than that? All right. And so we thought about that for a while. If we were more statistically inclined, we would have thought about what's the percentage overlap that would be relevant. And actually, a lot of work has gone into this, looking for what we might call the golden donut maybe 80% the same and 20% different or something like that, that would, and this work has gone on under the rubric of so-called faceted search, and it's very interesting work, but we had a different idea about how to go about doing this. And to illustrate the idea here, I'm going to show you another system we built called Beyond Broadcast. Beyond Broadcast would look at videos that you were watching, and then would automatically build, as Watson did for text documents, a web page relevant to the video that you were watching. And it did this actually at that time, not through image analysis, but by looking at metadata associated with the video. For example, the closed captioning data or other metadata associated with the video. And here we see a fellow named Alton Brown. Alton runs a television show, used to run a television show called Good Eats on something called the Food Network. And here he's talking about corn dogs, I'm not really, it's a hot dog on a stick put into cornmeal and deep fried. So it's kind of a stomach ache on a stick if you're not a vegetarian. I don't actually recommend it. It's the kind of thing that you will eat at outdoor fairs and carnivals and so on. It's not really something you'd cook at home or even really want. Kids kind of like it because it's strange food. And here he's talking about corn dogs, and we're getting a bunch of web pages about corn dogs. For example, the Wikipedia article about corn dogs, or the history of corn dogs, or maybe some commercial fryers that you could buy, and so on. So here, let me show you a web page. This is a web page about lasagna. This is a recipe for lasagna. Lasagna is an Italian dish, if you've ever eaten it, consisting of layers of big wide noodles with kind of sauce in between. Again, if you're a meat eater, and I apologize for the particular meat that's being used in this recipe, but it'll have a meat sauce there and in between, and so and cheese. So here is a direction for lasagna, and it turns out that lasagna is a very popular dish, and there are probably 5 million, or maybe at this point 20 million lasagna recipes on the web. So if I'm showing you a lasagna recipe, the question is, what else should I show you? I mean, should I show you another lasagna recipe? I mean, you already have a lasagna recipe, and almost all the other lasagna recipes I'm going to show you will be pretty much the same. Maybe I could show you a good accompaniments to lasagna, maybe a Caesar salad, or where you could buy a nice bottle of Chianti, an Italian wine, to drink with this. But really, if you were looking for another lasagna recipe, the point is it should be different in a certain way. It needs to be, for example, a vegetarian lasagna recipe, or a low-calorie or a low-fat lasagna recipe, or a low-salt lasagna recipe, or a seafood lasagna recipe, or a classic lasagna recipe, or a traditional one, or one that's quick and easy for a crowd. In other words, what you're looking for is something that varies in a certain systematic way from the recipe that I showed you. And this would be true of any recipe. If I showed you a recipe for stir fry, some kind of stir fry dish, perhaps you'd say like, well, I like this, but I'm a vegetarian. What's the vegetarian version of this? Or perhaps I want the halal version of this, okay, or the kosher version of this. So, or a healthier version of this with less fat in it. So these are all variations that make sense in the context of recipes. And we built a system that would go ahead and find alternative recipes using these kinds of variations automatically. So what this tells us is that determining the information that people will see in what form and in what order is an editorial judgment. And we want to make this editorial judgment explicit and visible both to the designers and engineers who build information systems and to the users of those systems. And here in this instance, there are these specific dimensions of similarity and dissimilarity. For example, vegetarian versus non-vegetarian, low fat versus not low fat, low salt versus not low fat, low carb, and so on, that actually are very relevant in cooking and in recipes that we could understand. Here's another system that we built along these lines. This was written by my student Jiawei Liu. Jiawei is now at Google. This was a system called Compare and Contrast, and what it did is if we showed you a news story, it would find a similar news story but involving different entities. So for example, here we have a news story about Oracle trying to buy the open source. Oracle is the big database company trying to buy an open source company called MySQL. And instead of getting lots of other news stories about Oracle trying to buy MySQL, here instead we have a story about IBM trying to buy buying a company called Glue Code, which was an open source company that did something else. And so here the theme being big tech companies buying small open source tech companies. And here we see the relationship between these two comparable stories. And the idea here was that by showing you this story, we would provide a context that would make it, that would sort of expand your context to try to understand the story you were originally reading, to provide other information that would you know, that would be relevant and kind of help you put the story in context. Here's another example. Here we're seeing a story about Israel's use of cluster bombs in the 2006 Lebanon war. And Watson, if we actually applied it, if we applied it to this story, would bring back 50,000 other stories on this same situation. But compare and contrast actually did something different. It brought back instead, for example, stories about the NATO's use of cluster bombs in Afghanistan, or the US use of cluster bombs in the Balkans during the war with Serbia over the Bosnia-Herzegovina challenges about 10 or 20 years ago. So again, we're putting this situation in Lebanon in context by providing you other cases where armed forces are using cluster bombs so that you can understand maybe better, was this a reasonable use or not a reasonable use of this weapon. Here's another version of this, a system called Local Savvy. Here we have a much younger Vladimir Putin visiting Iran, and we have an ABC News story about Putin's visit to Iran. Again, what are we going to get back if we apply Watson? Well, we'll bring back a lot of other news stories about Putin visiting Iran. But you know, what are we going to get back? New York Times stories, CNN, you know, The Guardian. In other words, an American user would get back basically other Western news sources. And the question becomes, where could I get a very different point of view on this news story? And the answer is, well, look, this is a story about Russia and Iran. So the place I need to go would be to Russian and Iranian news sources to actually understand this story from their perspective. And that's exactly what Local Savvy does. It actually looks for similar news stories or news stories on this topic, but actually from Iran. In this case, for example, here's one from a news site called alalam.ir about this visit. And so again, for example, we could imagine if it's a story about India, that rather than bringing back another CNN article or New York Times article, it'll bring back something from the Times of India or some other Indian news website. And so that's the idea, is to bring you back this kind of local information. Here's another system that we built that I really loved. It was called Spectrum, and the idea here was to bring back a spectrum of points of view on a question. But by point of view, I don't mean political point of view here. I mean different ways of knowing. For example, what is the business point of view on the situation? What's the technology point of view? What's the political point of view, or the legal or the health point of view, which we call epistemic dimensions in which the user might be interested. So for example, here is if we started with the EU Intel at the time, the American tech company that the EU was obsessed with was Intel, and we would bring back some blogs that are about from a technology perspective on the EU and Intel, whereas here we bring back some legal blogs on EU versus Intel at that time, and so we get back very different kind of points of view. And by the way, the technical challenge here was how to actually evaluate these texts without actually downloading them, because that would be the big bottleneck. And so it turned out that we did this in two different ways. The first is, it turns out that the snippet that was returned by the search engine was actually sufficient to categorize whether the blog entry was a legal or a technical one or a political one, and so on. So the second thing we did is we cached the different blog sites based on how this categorization had worked, because bloggers are typically consistent. In other words, a legal blogger is going to blog about law, not about technology. And so those were the two techniques we used to kind of make this thing work quickly enough. Here, finally, we have, and these were all built by Jiao Wei. Here we have another system built by my student, Francisco Jacobelli. Francisco is currently a professor at Loyola University in Chicago in their medical school. Here we have a story about BP, about the oil spill disaster in the Gulf of Mexico some number of years ago, in which a offshore drilling platform broke and began to spew just immense amounts of raw crude oil into the ocean. And here we have we're looking at this story from the Chicago Tribune about this, and here we're trying to find other stories that contain information about this situation that are not in the original story. In other words, information that's new to you because it's not in this story. And the question is, how do we actually do that? How could a system say, well, what's new in this story? That's a very challenging thing. And so we did what we often do in these situations. We tried to find kind of a cheap syntactic proxy that would actually work to enable us to detect something that was new information. Well, what would be new information? Well, new people's names would be new information. New numbers would be new information. New quotes would be new information. And these can be determined syntactically. We don't need a deep semantic analysis to understand that this number or this name was in this story, but not in the previous story. And that's exactly what Tell Me More did. It would find new stories about the same system using the kind of Watson analysis that we talked about earlier. And then it would actually do things like find additional actors. So here, for example, here we have a story from Channel 4 News. The chief executive of the American Petroleum Institute, Jack Gerard, said, "It is unnecessary and short-sighted to shut down a major part of the nation's energy lifeline while working to enhance offshore safety." So that's an additional piece of information, the point of view of the oil industry about this disaster. And here we have an additional numbers about the ultimately, the plan is to have 4 vessels collecting oil from the leak with a combined capacity of about 2.5 million to 3.4 million gallons a day. And then here we have additional quotes. For example, the hope is that we can slowly turn off the valves, close the capping completely, and then test pressure to see how the well is performing, says Thad Allen, the government's point man on the disaster on CBS's The Early Show. So again, we get this as a new quote. By the way, I remember this situation well, and Thad Allen did pronounce his name Thad, not Tad, which I always found interesting, but that's how he spelled it, so that's good. So this was kind of a cool system, but you may notice that all of the systems that we're talking about now look kind of similar. So these were all PhD thesis systems that were built by PhD students as part of their dissertation research. But ultimately, we began to see a pattern, and we had a big library of tools. So all of these things did content analysis and source determination and query formation and presentation. And we began to build a kind of tool set and a platform to support building these systems. And eventually we turned that into an entire toolkit and platform to make it easy to build these systems. So that's something that once took a PhD student 6 months of programming or a year of research to figure out how to do. We could actually get done in a couple of days or even a couple of hours. And in fact, that's exactly what we did. Once we built this platform, for example, we built the system TweetTalk. TweetTalk actually looked for tweets. This was when Twitter was friendlier to third-party applications. And in fact, when Twitter was called Twitter. So the idea would be to actually find tweets relevant to a news story. Here, for example, are tweets relevant. We are looking at a news story about a terrorist attack in Paris, France. And here we're finding tweets associated with that terrible attack. We built a similar system called Read It. I don't know how many of you are familiar with the website Reddit, which is a place where people go to discuss and argue almost everything in the world. And here we did a similar thing. We called this Read It. If you look at Reddit threads, you'll find that they very often refer to news stories. Here we wanted to go the other way around. Let's start from a news story and find Reddit threads that are relevant to that news story. That's why we called it Read It. And so here, for example, again, we have a web page about about the attacks in Paris on the satirical magazine Charlie Hebdo for what were deemed sacrilegious cartoons about the Prophet Muhammad. And here we see a lot of Reddit threads that are relevant to this terrorist attack. including this Reddit thread, which is in solidarity with the satirical magazine Charlie Hebdo. It's called Je suis Charlie, I am Charlie. And here we have this web page, this Reddit page talking about discussions and showing points of view and live updates about this tragedy. And so that was the idea here. And this was built in a few hours. And so I'm done with this section of the talk. Here again, the main point was that we're building these automatic information systems, and we're building them on top of conventional information retrieval. I mean, today we might build them on top of vector databases using word embeddings, and they might work slightly better, but they worked pretty well using IR too. And in fact, since the underlying search engines that are in the world right now are primarily still using standard information retrieval, this technique makes a lot of sense. But I will pause briefly to see if there are any questions about this line of discussion. Okay, then I'll just continue. So I'm going to shift gears now and talk about a bunch of systems. And by the way, just to make it clear, this entire talk is about stuff that I built, or rather that my students have built in my lab over the past few years, and kind of to sort of show you the range of things that it's possible to build using a variety of underlying AI technologies, not just LLMs or generative technologies, but also, again, information retrieval or standard machine learning, which is what we're about to talk about here. So here we're going to talk about building computational journalism systems on top of text analytics that use standard machine learning methods, categorization. And these are systems that play to the machine's strengths. In other words, they treat natural language more as data and less as a medium of communication. And the technology that we're talking about here would be things like nearest neighbor, or k-means nearest neighbor for clustering, or we might be talking about the use of SVMs or support vector machines or random forests, or a variety of other kinds of categorization techniques that we might use in trying to understand the nature of a particular document and what it might mean or what we might do with it. So here's a system that we built called Tweetcast 2012. We built this, as you can see, about a dozen years ago, and we built this during the U.S. presidential election between Barack Obama. This was his re-election campaign after his first term. And at that time, Joe Biden was his vice president and vice presidential candidate. And he was running against the Republican nominee at that time was a fellow named Mitt Romney, and his running mate was a guy named Ryan. I actually don't remember Ryan's first name. But anyway, it was Romney Ryan versus Obama Biden. And the idea of Tweetcast Your Vote is if you give us your Twitter handle, and again, this was done at a time when Twitter was much more friendly to third-party applications and researchers, it would automatically predict who you were going to vote for based on your tweets. And again, we used a very standard text classifiers to actually do this. And here's an example of Tweetcast in action. So for example, well, actually here is, these actually are lists on the left of the terms that were most predictive of being a Romney voter on Twitter. And on the right, we have the terms that were most predictive of being an Obama voter. And if you look at these terms, you will no doubt notice that the terms on the right include a lot of curse words. Perhaps the most anodyne of which would be bullshit. And there are a number of other curse words that are a little bit higher voltage than that one. And there are other words here like equality or women's that might actually make sense to, might be relevant to a Democratic voter. They concern issues that are relevant to Democrats. And on the left, we see terms perhaps relevant to Republicans, terrorism, for example, or liberals. You know, the use of the curse words actually is a good example of one of the problems with statistical machine learning, and this includes generative AI and LLMs, which is we don't always understand why it is that they actually do what they do, because they seize, in this instance, it's clear that there is a correlation between the use of these curse words and being an Obama voter in 2012, but it's not clear why, right? I mean, it isn't clear why Democrats might actually be cursing at higher rates than Republicans online. And I have some theories about this that I could imagine, but ultimately it's just not, it just happens to be correlated. And so the machine system picks up on that correlation. By the way, the main question that you should have about this system isn't the underlying technology. Here, I believe we used an SVM. An SVM was the main underlying system that we used. But what you should be asking is, how did we get the data? In other words, to build a machine learning system like this, you need labeled training data. In other words, we need sets of people's tweets on the one hand and who they voted for, who they were going to vote for on the other hand. And how did we figure this out? And the brainwave that we had, which was kind of interesting, and maybe this is actually a good example of kind of how research gets done. My student who built this, by the way, was Sean O'Banion. Sean is now at Google as a senior engineer. Originally, Sean was building a very different kind of, this is a kind of a recommendation system, really. He was building a news recommendation system, and he said, we were trying to figure out how to evaluate the system. In other words, it was going to look at your tweets. It was going to try and categorize them. I mean, were you interested in the economy? Were you interested in India? Were you interested in the Middle East? Were you interested in cooking and so forth? And then bring back news stories that were relevant to your interests as kind of determined by your tweets. But we had a hard time understanding how to evaluate this system because we couldn't do a large user study. We just didn't have the capacity to do that. Sean came in one day and said, wow, I have an idea about how to do this. Like, if somebody tweets out a link to a news story, then we know that they were interested in that news story. So maybe we could go back and look at their tweets prior to the time that they tweeted that out and ask if we would have predicted, if we would have recommended that specific news story to them or a similar news story. And the minute he said this, I said, that's all we need. Once we have the link between their tweets and the news story, we don't even need any other data. We don't need to actually do a topic categorizer or anything. The label will be that news story. Other people who tweet like this person recommend that news story to them, at least within a certain time frame. Okay, and that's what we did here for Tweetcast as well. I mean, and the way we found out who you wanted to vote for is that, of course, Twitter is a system for natural language expressions. And people would say things like, I love Barack Obama, or I'm planning to vote for Mitt Romney. And so we discussed regular expressions earlier. We used a regular expression text, sort of text patterns to actually identify tweets that had phrases like, I'm going to vote for Mitt Romney, in the tweets that had those in them. And then we'd gather another 100 tweets from that person and we'd bundle them up and say, the person who tweets like this is going to vote for Romney. And this turned out to be quite effective, actually. Interestingly enough, Sean went to this work won a Best Paper Award at a conference on social media analytics while Sean was a graduate student. I was very proud of him. When he went to give the talk at this conference, the person prior to him was giving a talk on a similar topic about about trying to understand people's political points of view from their social media activity. And the fellow said, well, of course, people don't tell you who they're going to vote for. And then Sean got to get up and say, well, actually, people do tell you who they're going to vote for. At least enough people tell you who they're going to vote for that you can use that to predict who other people who are going to vote for who haven't divulged that information. And we use this same approach for a variety of things. Here we have a book recommendation system where when people tweeted out that they loved a certain book, we would actually use that to determine what kind of books would you like to read. This system, BookRex, got about it used, again, it was a two-layer classifier. It used first SVMs and then nearest neighbor. And about 60,000 people use the system, which is not much for the internet, but it's pretty big for an academic system. And about 15% of them actually clicked through to look at the book more closely. We were not clever enough to actually build an affiliate marketing scheme here so we could figure out how many people actually even bought the book. But 15% is a pretty good click-through rate for a recommendation or advertisement. So we were pretty happy with this system. And we built a whole bunch of systems like this. Here's another one built by Sean called LocalRex. This is a map of downtown Chicago. The blue on the right is Lake Michigan. The blue lines in there are the Chicago River. Here LocalRex recommended local restaurants, bars, shopping venues, and cultural sites to you, again, based on your tweets. And again, we use Twitter data to actually do this. And it was hard to understand how to evaluate this, so we actually used Yelp as our baseline. And what we found is that for popular establishments, it was about the same as Yelp. And that makes sense because popular establishments are popular because a lot of people like them. But what we found is that for local, or less popular places, in other words, things that represented niche interests, perhaps you really loved South Indian food, and in the United States, that might be a less common preference than it would be in India. It would actually did a better job of recommending places to you based on these niche interests of yours than Yelp did. And then finally, again, the same thing happened, is that we had Sean had built a number of these systems as part of his PhD thesis. And then we had at one point during one quarter, I had an undergraduate team build a student club recommender for Northwestern students based on their tweets. And we didn't know how to evaluate this, so we took famous people and we asked what clubs at Northwestern would be recommended to them. So, for example, Hillary Clinton, it would recommend Northwestern Democrats, college Republicans, and the Northwestern Political Union. Julia Louis-Dreyfus, who was a famous actress who was a Northwestern alum, it would again recommend NU Democrats, also the Jewish Theater Ensemble, Northwestern Flip Side, which is a satirical magazine, Lipstick Theater, which is a women's theater group at Northwestern, the Dolphin Show, which is a musical theater group at Northwestern, and so on. For Bill Gates, it recommended things that make a lot of sense. For example, Unite for Sight, which is a global health alliance, Engineers for a Sustainable World, Design for America. These all seem to fit Gates's interests. It also recommended the sorority Alpha Chi Omega, which is for women students, but of course the system is unaware of this when it made this recommendation. And that's really all we could do to evaluate this system, because again, we couldn't do a large-scale user study in the course of the 10-week term that we had. But again, having built a bunch of systems like this, we again built a platform. We had a set of tools to make it easier to build these things, and we had we understood what the control flow and the data flow looked like. And so we actually built a system that would automatically build a Tweetcast application. If you simply gave it the names and websites of two candidates in a district, it would automatically build a Tweetcast system that would actually predict who somebody was going to vote for based on their tweets. And we called this predictive politics. So here it would build a model. It would actually gather the data automatically. It would build the model, and then it would, after about a day building the model, it would mail you back a link to a website that it had built automatically to actually do this kind of task. And we, by the way, it was hard again to evaluate this system. We did a point where we actually decided, well, it doesn't have to be about political candidates. So we did a version where we asked the question, which entrepreneur do you like better, Elon Musk or Jeff Bezos? And then we looked to see what would Peter Thiel say, and Peter Thiel, according to his tweets, would prefer Musk, which made sense to us, and Bill Gates, according to his tweets, would prefer Bezos, which also made sense to us. So that's really all we could do in terms of evaluating that particular application. Any particular system, of course, you'd have to evaluate more closely. Okay, are there any questions about this line of work, the use of sort of standard machine learning as the underlying substrate for these kind of computational journalism systems? Okay, if not, then I'll go on. So I want to sort of switch gears now and talk a little bit about narrative analysis and computational journalism. Our goal here, actually, a lot of this work is similar to the previous work. Our goal here is to analyze news stories in terms that focus on the narrative that are orthogonal to highly studied dimensions of text analysis. So if you've ever done any text analysis or read any papers on text analysis, you'll notice that they focus on very similar things. For example, sentiment analysis is a very common application for text analysis. In other words, is this a positive or negative tweet or a positive or negative statement about a person or a product? And obviously marketers and market researchers are very interested in this sentiment analysis. Another kind of analysis is called topic analysis. Like, is this story about politics, or is it about biology, or is it about China? All right, and so you have these kind of topic analysis systems, and almost all text analysis systems that you see fall into one of these two categories, either sentiment analysis or topic analysis. We were interested in kind of, if we were going to do this kind of work at all, I mean, it was not that interesting to us to build another sentiment analyzer. And so we thought about other kinds of analysis that we would do. So here's an analysis that we did called about categorizing election news. So in the United States, at least, and I'm sure this is true in India as well, election news stories typically fall into a number of different frames or genres, three in particular. They can be policy stories. In other words, what are the policy proposals or the platforms of the candidates who are running for election? They could be stories about the candidates themselves, for example, their biography or their character. Or finally, they could be what are called the United States horse race stories. A horse race story is not about the candidates or about their points of view. It's about the state of the race itself, of the election itself. In other words, who's ahead in the polls, who's behind in the polls, who has raised more money, who has more people working on the ground in Iowa or some other location. And these horse race stories actually make up the majority of news stories in the United States about an election. Will always be about this, about the polling, or about money, who's raising it, or about endorsements, who's been endorsed by whom. And there's some evidence actually that horse race stories promote cynicism among the electorate, that people kind of turn off because of these news stories and become less interested in the election because it's all about the horse race. It's not about what the election is really about for them. And so we actually wanted to build a system that would detect horse race stories. We tried a number of approaches using the simple bag of words representation, which is what information retrieval uses. This is simply a term vector. In other words, a term histogram of the document. How many words, what words are in the document, how often they appear in the document. And actually, as it turned out, every approach to machine learning that we tried didn't work very well. And the best results we got were using hand-built term sets. Even here, we didn't do very well. The precision was 0.7. What that means is 70% of the time, if we said it was a policy story, it was a policy story, but 30% of the time, it was not a policy story. And 69% of the time, if we said, if it was a policy story, we would identify it as a policy story. But that means that 31% of the time, we would identify it as something else. I expect that this is a case where more sophisticated representations and algorithms, for example, using word embeddings could do considerably better if we went back and rebuilt the system using that technology. And we actually did a number of things with this. One thing we did is we built publication report cards where we went through different news sources in the United States and said, what percentage of their stories about, for example, here's stories about the 2017 Alabama Senate special election. This was a senatorial election in the state of Alabama. How many of the, what percentage of your stories were horse race stories? Here we see that CNN, for example, 50% of its stories were horse race stories. Whereas, by the way, if we went up to the Washington Post at the bottom, 93.8% of its stories were horse race stories. That was one way of thinking about this. Another thing that we did is to offer readers an alternative. And so the idea was, if you're looking at a news story about the election and an election, and that news story is a horse race story, maybe we could provide another story to you that was about the character or biography of the candidates, or maybe about their policies instead of. So here we have an election in Arizona a number of years ago between Kirsten Sinema and a woman named McSally. I forgot her first name. McSally was the Republican nominee, and Sinema was then the Democratic nominee. She subsequently has left the U.S. Senate, but she was a rather quirky person. This was a horse race story from Fox News about early voting and what it means for the election. And what we did is we retrieved another story about this election that was not a horse race story. How would McSally and Sinema vote on the Kavanaugh nomination? At this time, Brett Kavanaugh was a nominee for the Supreme Court. At that time, he eventually was confirmed. He was a somewhat controversial nominee. And so this actually would tell you a real story about how these people pledged to vote on that case. And then finally, we built a very interesting system that I really loved called Heroes, Villains, and Victims This system was a system to actually look at a news story and not understand it deeply, but understand who is being portrayed in a positive or negative light. So you can think of this as a very kind of specialized form of sentiment analysis. But the particular roles that we were looking for is in this story, who's being portrayed as the hero in this story, who's being portrayed as the villain, and who's being portrayed as the victim. So here we have a story about President Donald Trump in his first term as president 4 years ago or some number of years ago, visiting France and meeting with Emmanuel Macron, the president of France. And this is a New York Times article, and our system indicated that the way this story was written, it was written in such a way that it kind of was written with the theme that Macron has rescued France from Trump. So Trump is being portrayed as the villain, Macron as the hero, and France as the victim in this story. And the idea being that perhaps we can find other stories that show the situation in a different light with different kinds of with the protagonist playing somewhat different roles in the story. Okay, we really are done with that section now, and I want to move on to telling stories at scale. So this has really been the main body of my work over the last 10 years. It was the work that led to the formation of the company Narrative Science, which was the first company dedicated really to storytelling from data. The company was eventually acquired by Salesforce in its Tableau unit, and the work goes on. I was a consultant for Salesforce for a number of years after the acquisition, although I no longer consult for them, but that was a lot of fun too. And here the idea is that if we think about data science, and a lot of you are probably thinking a lot about data science, at some level, the idea of data science is to help people make better decisions by actually, gathering large amounts of data to understand statistically what makes the most sense in the circumstance. And the point that we were trying to make is that there's no point in gathering and analyzing all the data that we are gathering and analyzing if we can't convey the results to people in a way that they can understand and take action on. So we have to actually be able to explain the results of the data analysis to you if you're going to be able to use it. So this is one of the reasons why data visualization, and many of you may have been studied data visualization or be interested in studying data visualization, this has become an extremely important topic in computer science, specifically because of this, because people think of visualizations, charts and graphs as the main way of conveying numeric information to people. And so that became kind of the method for this. We actually got interested in the idea of, well, what if it's actually not visualization, but narratization? In other words, we're going to tell you a story about the data that will automatically convey key insights from those data to you, okay? And to make this work, we needed to find a very powerful and useful sweet spot in terms of task and domain and context in which we could engineer a solution. Now, the solution I'm about to show you was not using LLMs. And actually, of course, I've done a lot of work subsequently on the use of LLMs for data storytelling, and they have some very powerful traits, but some very problematic deficiencies, most spectacularly their propensity to make stuff up, otherwise known as hallucinations. If you're looking at a bunch of data to try and understand what it means for your health or your business, the last thing that you want is for the machine to be making something up that isn't grounded in the truth of the data that you have gathered. I mean, that's the whole point of data science, is to actually base decisions on hard facts about the world. You aren't supposed to make something up, and you don't want the LLM making something up either. And so that's actually proven highly problematic in building LLM-based data storytelling systems. And there are some additional challenges as well, which I'd be happy to go into during the question and answer session, like what makes it difficult, why you can't just take Gemini or Claude or GPT-4 and point it at some data and ask it to write a story and expect that you're going to get good results. Sometimes you'll get good results, but very often you won't. And that's actually a point of current research. Here's the punchline of the system that we built. So here, for example, we have a bunch of data about a hockey game. This is a hockey game that was played between two high school hockey teams or maybe smaller hockey teams in Texas, in the Rio Grande Valley Killer Bees versus the Laredo Bucks. And these data were gathered from the hockey game, and our system would take these data and write this story. The Rio Grande Valley Killer Bees were firing on all cylinders against the Laredo Bucks, and when the final buzzer sounded, Killer Bees emerged with a 6-3 win. Zach Pearson was all over the ice for Rio Grande Valley as he tallied 2 goals and 1 assist in the win. Pearson scored the first of his 2 goals at 5:23 into the first period to make the score 1-0 Rio Grande Valley. Brandon Campos picked up the assist, and so on. And this is not a bad story at all. And so we did these kinds of stories. We did sports stories using this technology. So again, the input to this technology is tabular data like these kinds of data right here. Okay. And we would write a story like this from these tabular data. We also did business stories. For example, here's some business data about Red Hat. And we would actually write, we actually wrote a quarterly earnings previews for Forbes magazine, Forbes.com, using these kinds of data. So here's a story about Red Hat. Here's another earnings preview about Home Depot, based again on tabular data about Home Depot. The first prototype for this system was built at Northwestern. And here we have, it was for baseball games. Baseball, as you probably know, is similar to cricket. Although to be perfectly candid, all of my efforts to understand cricket have come to nothing. I mean, I get that there's a ball and a bat and there's pitching and catching, but other than that, I find the game very difficult to understand, even though it's in that sense very similar to baseball. But for some reason, I can't grasp the game. In any case, and this could be done and probably has been done for cricket as well. Here we have some statistics about a baseball game. It's a baseball game about the Chicago White Sox playing the Seattle Mariners in Seattle. And here we have some data from the game called the line score and the box score. And we also have the so-called play-by-play data, which is, that, X came up to the bat, they struck out. X came up to the bat and they hit a single, which means they got to first base and so on. So we take these strings of kind of numerical and quasi-numerical data, and we generate a bunch of underlying features. For example, what were the most important at-bats in this game? Who were the best players? Who were the most important at-bats? And having done these analyses, we then write the story, and the story looks like this. Down to their final, last out, Griffey saves the Mariners, Seattle. The Chicago White Sox had the Seattle Mariners down to their final out, but Ken Griffey came through with a single to drive home the winning run in Seattle's 1-0 victory in a 14-inning marathon on Wednesday at Safeco Field. After Adrian Beltre singled and Jack Hanhan walked, the game was tied when Griffey came to the plate against reliever Tony Pena with 2 outs and runners on first and second. He singled, scoring Beltre from second, which gave the Mariners the lead for good. Seattle and Chicago played 14 innings. The two teams combined to have 10 pitchers pitch in the game. So this is a story which is very similar to what's called the AP short recap. The AP is the Associated Press is a newspaper, is a kind of consolidated newspaper service in the United States and worldwide. And so this is very similar to what's called the AP short recap, which is typically written by a human being after a game. And so this was the first system that we built, and we were very excited by the results because they were pretty good. And actually, I don't know how many of you know about XKCD, the online comic strip, but they eventually got onto what we were doing, and they had this cute comic. A weighted random number generator just produced a new batch of numbers. Let's use them to build narratives, and this was called All Sports Commentary. Strangely enough, we never did that. We never did use random data to build random narratives. We should have tried that. So one question might be, why story? So here's some tabular data. I like to say that one of the things I like to say is that even little data is big data. So this is a very small piece of a spreadsheet. It's got 2 rows and, I don't know, 10 columns or something like that. But even this is kind of overwhelming for a human being. Like when I read this is hard for me to understand. Especially if I'm not a business person, it might be hard to understand. And so instead of showing me this small table from a spreadsheet, maybe I'm going to build this graph for you. So here's a graph, because one row is about gross profit and one row is about sales. So here we have graphed gross profit and sales on a graph, and you might be able to understand the story in this graph. I actually didn't. I only see one thing here, which is that they're both going up, which seems good to me. As it turns out, the story in these data is not a good story because although they're both going up, sales is going up faster than gross profit is going up. In other words, the profit margins of this company are going down as sales go up, as sales scale. And what you want to see in a healthy business is exactly the opposite, that profits margins get bigger as sales go up. Okay. Over the past 8 quarters, here's the story that we wrote about this. Amgen Corporation has seen a steady increase in both sales and gross profit. During this period, however, 2 trends have become apparent. While sales have increased, there has been a steady decrease in margins, which should be cause for concern. Okay. In addition, while we have seen quarter-to-quarter increases in both sales and gross profit, each of these metrics is decelerating. In other words, although the first derivative is positive, the second derivative is not positive, indicating that the business is experiencing a slowdown. So neither of these were obvious to me looking at the graph, all right? And that's why a story is necessary. So just to sort of make the point, stories highlight, connect, and summarize critical aspects of a situation. They explain what's going on. They convey trends, causes, and they may even make recommendations. They can provide context, and they make data meaningful. All right, and that's really why data matter. And this, again, is the point that even little data is big data. Now, a point I want to make here is that if we started with these data and we were turning them into text, here's some text about these data. If you look at this data, in Q1, sales were $12.6 million, gross profit was $9 million. In Q2, sales were $15.6 million, gross profit was $12.4 million, ... This is not a story. This is completely useless. This is actually even worse than this. I mean, this is actually at least a table that you can look at and compare. I mean, this is really completely useless. And the point that I'm trying to make here is that simply turning numbers into text is not storytelling. Okay, storytelling requires selection. The core of storytelling is not natural language generation in a narrow sense. It's not text generation. The problem is much more what to say rather than how to say it. In other words, a storyteller needs some kind of model of what matters more, of what the listener or reader needs to know. Okay, in other words, a storyteller needs a model of the questions that the listener or reader has about the situation or should have. And that's what the story needs to address in the case of data storytelling. In other words, a data storytelling revolves around questions. And it's the relationship between the questions and answers that the story, each question should have an answer, and each answer may raise additional questions, which the story should then go on to answer as well. And that's what makes the story coherent. I also got very interested in this time at what we called narrative analytics, which, your narrative goals determine the data analysis and even the data that you need. And what we saw really is that stories often embody very high level patterns or themes. So, for example, in sports stories, we have stories like a comeback victory. The minute I say to you this was a comeback victory, you have the picture of the whole situation in your head. Fading, that means sort of, unable to keep up. Or in business or planning, low-hanging fruit. This means high-value things that you can do that are easy to do is what low-hanging fruit is. So these kinds of themes make data coherent. They characterize situations very usefully, and they're very efficiently communicated and effectively grasped through these small phrases. And so we were very excited by these kinds of things. I mean, another kind of phrase like this would be canceled each other out. Like you might have a story in which profit in one sector of your company went up and or revenue in one sector of your company went up and revenue in another sector went down. At the end of the quarter, you could say, well, sales were flat, but that doesn't tell the story. What you really want to say is that, sales in the Northeast were up while sales in the Southwest were down and they canceled each other out. That's a different story from sales were flat across the whole country. Now, I want to take a brief aside here to say a little bit about how we made this system work, and we're coming to within 10 minutes of the end of my time. And again, I do apologize for the fumbling at the beginning. Here's how this system worked. At the bottom, we started with the data. We did some data analytics, okay? And then we answered some questions about based on these Actually, the way the story started was the opposite way. We started with in the middle with the pragmatics. What does the reader need or want to know? What questions must the story answer? And that drove in two directions. One, underneath, what are the answers to the questions that we're looking for? What analytics do we need to get those answers? And what data do we have that those analytics need? And then finally, at the other end, how do we organize all the information to actually build a story? What rhetorical structure do we need? And so the system actually operated bottom up, but it was organized from the middle out from the perspective of how we built it. Now, this might not look the way you expected it to look. You might have thought that it looked like the data come in, an LLM looks at it, a machine learning system looks at it, it generates the story. That's the end of the process. So now I have a question for you about self-driving cars, and this may seem irrelevant, but bear with me. I'm going to ask you each to consider the following question. I had this opportunity a number of years ago to talk with some big self-driving car experts, including the head of Nissan's self-driving car lab in California, the head of Uber's self-driving car lab in Toronto, and the head of the self-driving car lab at Carnegie Mellon University. They were on a panel that I saw, and I spoke with each of them after the panel. And I was trying to think of a question that would help me understand how these systems work. And I came up with the following question. You are in the middle of and this has been formulated for the case of India. You are in the middle of a 3-lane road in your direction. You need to turn left shortly. You know this because Google or some other mapping system is telling you need to turn left. Before you turn left, you need to get into the left lane. We all know this as drivers or passengers, that the car has to get into the left lane before it can turn left. Now, the question is this rule or behavior learned or built in current self-driving cars? And I'm not going to ask for a vote here, but I ask each of you in your head to think, well, what do you think? Do you think it's learned or built in current self-driving cars? So when I ask my students this in Intro to AI, most of them say they think it's learned. Actually, it's not learned. It's built in. Okay. So this actually rule is not learned. Self-driving cars have this rule, but it's actually built into their architecture. And that might surprise you. And the reason it might surprise you is you're thinking to yourself, well, if this is built in, there's got to be 10,000 other things like this that's also built in. And that's right. That's actually true. There are 10,000 or 100,000 other things like this that are also built in. In other words, you might have thought that self-driving cars work like this, where we have the input as perceptual data going to some large neural network or other statistical learning mechanism, and the output finally are driving behaviors. And there are people who are trying to build systems that work like this, and there might be some advantages to doing that. Although to be 100% clear, this could not be done in the real world. It could only be done through simulations, because a machine trying to learn this way would get into a lot of accidents to begin with. So, by the way, this is clearly not how people work, how people learn how to drive, okay? In fact, self-driving cars work like this. They're pretty complicated structures that look a lot like a very standard AI robotic control theory stack. Okay, at the bottom we have, or control system stack. At the bottom we have perceptual data, we have perception. Perception feeds into prediction and tracking. That feeds into planning. Planning feeds into plan execution and monitoring. And finally, that produces the driving behaviors. Now, each of these subcomponent systems might use a lot of machine learning, or might indeed use a lot of neural networks, but the system as a whole is a lot more complicated than that. Back to, and so actually the way our system, that's why our system looks more complicated as well, that we have, that's why our system looks like this, okay? It doesn't look like this because, it kind of wasn't clear that it could, and indeed, it's not even clear that self-driving cars could work this way either. Once we had the system built, we did a lot of things. I mean, I hope it's clear to you that the reason for having an automatic system to write stories from data is to be able to write stories at scale. In other words, you don't need this to write 1,000 stories or 100 stories. People are fine for that. You need it to write millions or hundreds of thousands of stories. So here we partnered with ProPublica, which is a nonprofit news organization in the United States, where we took civic data about high schools in the U.S., their academic rankings based on test scores, and then also the socioeconomic data relevant to their student population. And we wrote 52,000 stories about almost every public high school in the US based on Department of Education data. So for example, here's a story about Evanston Township High School. This is the high school in Evanston, Illinois, where Northwestern is located. It's the high school that my children went to. And we have a variety of things here. For example, Evanston Township High School is below the state average in terms of the percentage of its students who qualify for free or reduced price lunches. On average, 40% of the students in Illinois qualify for free or reduced price lunch programs, whereas 39% of Evanston Township High School students do. And then it would actually try to compare the performance of ETHS, as it was called, with neighboring high schools, and say, well, how does it compare in terms of its of the population it's serving, and how does it compare in terms of the educational outcomes, like how many advanced placement courses are students taking, or how well are they doing on standardized tests, and so on. And eventually, of course, we did a lot of business data from this. We actually did narratives for Power BI. That's a Microsoft product. For Qlik, another visualization product, and of course for Tableau. And they eventually, Tableau is now owned by Salesforce, and they eventually acquired us. But the thing I'm actually most proud of here was the work we did on youth sports. In the United States, youth baseball is called Little League, and so here we have a Little League story about a game in Richmond, Virginia, the Richmond Rampage. A superb effort by Cat Morris and Richmond Rampage lifted Richmond Rampage to a 6-0 win in 7 innings over Blue Ridge Sudden Impact on Sunday at Darden Tote, Charlottesville. Morris kept Blue Ridge Sudden Impact off balance while she was in the circle. Blue Ridge Sudden Impact managed just 1 hit off of Morris, and so on. So the thing about a Little League story like this, and by the way, we get the data because there's a company in the United States called Game Changer that has a smartphone scoring app. So if a parent or a teacher or a coach at the game uploads the data about the game, then we got the data and we could write a story. And we wrote hundreds of thousands or millions of Little League stories by machine. And the point being that you can't, it's, maybe 2 people or 10 people are going to read this story. For example, Cat Morris's grandparents or friends might be excited to read this story, but nobody else will. All right. And that's why we need a machine to write these stories, because it's not cost effective to do elsewise. Eventually, we got a New Yorker thing about us. Did your dad or a computer algorithm write this? This was written by a computer algorithm from Narrative Science, a company your dad thinks you might want to work for, which is why he sends you every article about how innovative the AI-powered language generation platform is, even though it's literally the opposite of what you do and against everything you believe. Well, I hope it wasn't against everything that everybody believed. I'm now going to move finally. I don't really have time to take questions about this, and I apologize. Somebody tell me, I mean, we're at 1 hour and 13 minutes, but of course we started a little late. Can someone tell me how many more minutes I have?
So you take your time. I guess we still have 5 to 10 minutes if you want to get.
Okay, I'll move through this quickly as I can, and I apologize for the fumbles at the beginning.
It's all right.
Finally, I'm going to turn to the question of conversational interaction, and here I actually do, and my students and I are using LLMs to do these tasks, and I'm trying to understand really how to understand and improve their semantic competence, and I'm going to show you what I mean by that. We've built a lot of conversational recommendation systems that work like this. They're very different from the Netflix model, for example, of conversational recommendation, or of recommendation general, which is not conversational. The idea here is the concierge model. You provide some initial constraints. The concierge makes a recommendation. You critique those recommendations. You say what you don't like about them or what you do like about them. The concierge understands your needs better and makes a new recommendation, and you loop until you're good enough. So here's an example where, for example, we're making a recommendation where of the Capitol Grill. What don't you like? It seems a little tacky for the price. I hear you prefer a more stylish place, and then it recommends some other places to you. So our system worked like this. And the architecture of the system was, what we realized was we needed to take this negative critique, it seems tacky, or this place seems very loud, or I don't see any vegetarian options. So if you go if you're looking at a restaurant, a recommendation, you say, I don't see any vegetarian options, what that means is I need a restaurant that offers vegetarian cuisine. all right? You didn't say that. You offer a critique. I have to turn that into a positive preference. And so there's a pragmatic inference that has to happen here where you turn the critique into a positive preference. You look for arguments in customer reviews that match that preference, and you return the top match, okay? You might want to check out Shanghai Terrace. Here's what a previous customer wrote: really amazing rooftop dining area, one of the best. And so this is what I mean by pragmatic common sense. You have to make this inference from the negative critique to the positive preference. In this case, I want a restaurant that offers vegetarian cuisine, okay? And we used statistical language models, i.e. LLMs, to perform this inference. In other words, we gave them prompts like, in this case, they did kind of what's called few-shot learning, or it looks too spicy for me implies I prefer milder food. It looks too greasy for me implies I prefer lighter food. I don't eat meat implies I prefer, and then the machine would say salad. I don't like fast food would turn into I prefer healthy cuisine. I don't eat fish. I prefer chicken, pork, lamb, duck, or beef, and so on, okay? And so it would then match the preferences that it inferred to a review. And here we're using language models to perform this common sense inference. And the point is, how do we go from M&S has great seafood to if you like seafood, you should go to M&S, which is really the point of this thing. Now, in this system, there are two ways to do this. One way is to do what self-driving cars do. In other words, let's use language models as components in a much larger heterogeneous system, and that's what we did above. The recommendation system we built is not a statistical machine learning system. It has a very clear deterministic algorithm, provide a recommendation, get the critique, turn the critique into a positive preference, look for reviews of other restaurants that meet that preference, make another recommendation, and loop until the user is satisfied. But the components themselves actually did use LLMs. The alternative approach is to try and push that control structure, that decision-making structure, into the LLM itself, and ask, in other words, teach it how to carry out those subtasks and how to compose them to carry out the task as a whole. And we do this as well. For example, let's think about decision-making as a task. You're trying to decide whether to go to Miami or Minneapolis on vacation. The system needs to know certain facts. For example, that Miami has an average temperature of 75 degrees Fahrenheit, whereas Minneapolis has an average temperature of 50 degrees Fahrenheit. It needs to compare them and therefore realize that Miami is generally warmer than Minneapolis. It needs to know or learn the user preference. In other words, I like warmer weather. And it needs to combine these finally to make the decision or recommendation, I should go to Miami. All right. And that's the decision making. And so what we did is we actually built an approach to using LLMs, which we called compositional fine tuning, where we decompose the task into its component inferences as illustrated above. And we explicitly fine tuned a language model on those inferences. And in fact, we found that it works as well or better than chain of thought inference, which you may have heard of. And it works much better when using smaller and cheaper models. So I'm not going to go into the details of this except to show
Sir, you are not audible.
Am I audible now? Hello?
Yes, sir.
Yes, I am.
Yeah, sorry about that. I don't know what happened. Okay. Mainly, if you look at this, the main point is simply to show you that on cheaper and smaller models, the system actually, our approach of using compositional fine tuning actually worked as well as on a very small model. Curie worked as well as a chain of thought did on a much larger and much more expensive model, and much better than chain of thought did on the cheaper model. And again, similarly, above is the case of travel domain, like what city should I go to, and below is local dining and recommendation. And you'll notice, by the way, that travel does much better than local dining. And I think the reason is obvious, that LLMs will have much more information about world cities than it will about a particular local restaurant. And so this is really an instance of the fact where something like what's called retrieval augmented generation would absolutely be necessary. It would be important to actually read about these restaurants to make recommendations about them. And our system did that to some extent, actually. Okay, let's go on here. So I'm gonna make a general statement about this. Now, 2011 was really an amazing year for AI. 2011 was the year that IBM's Watson beat Jeopardy. 2011 was the year that Google revealed that it had self-driving cars driving around the Bay Area in Northern California. 2011 was the year that Apple Siri first had conversations with people. They weren't very deep conversations, but you could talk to your cell phone and get something useful out of that. And actually, 2011 was the year that the company I co-founded, Narrative Science, wrote 400,000 Little League stories. Now, everything that happened in 2011, I expected to happen much earlier, maybe 20 years before, maybe even 25 years before. And a lot of other people felt that way too. And looking back at the history of AI, in 1960, Herb Simon predicted that a computer would be world chess champion in 1970. That didn't happen. And when it didn't happen, there was a lot of criticism of AI, both within and without the field. Deep Blue, again, an IBM system, finally defeated Garry Kasparov, then the world chess champion, in 1997. So Simon was off by 27 years. And the question I think we have to ask ourselves is, does that matter? And I think the answer is no, it doesn't matter. I mean, ultimately the prediction came true and a computer is the world chess champion. So what changed? Well, first of all, data, the internet, cheap memory, and vastly more computation, technical advances, but note that many of these had their roots in the 1980s and even earlier. The first neural net model was actually put forward in 1943 by McCulloch and Pitts. The first learning model using neural networks, the perceptron, was built by Frank Rosenblatt in the 1950s. Deep learning and backprop actually started in the 1980s with Hinton and McClelland and Rumelhart at the University of California, San Diego. All right, and so that's 40 years ago, really, and 60 years ago that this, 40 and 80 years ago that this work started. And so we were off by 20 or 25 years. Does that matter? My personal experience of how this feels is, wow, this is taking a long time. Wow, this is taking a long time. Wow, this is taking a long time. Wow, that was fast. And I now realize that this is what it feels like to live inside of an exponential. Everything seems like it's taken forever until all of a sudden it seems like things happened overnight. But that's how exponentials are. They have this hockey stick look where nothing happens and then bam, it's like a rocket ship. So that's really, I think we're going to have to get used to that feeling all the time. Now we have LLMs. As I mentioned, based on the perceptron model from the 1950s, multi-layer neural networks started in the 1980s, deep learning in the 2000s. Google Translate in 2016. Finally, ChatGPT was launched in 2022. Amazingly fluent, surprisingly intelligent text generation, even code generation. But the last mile is the hardest. The first DARPA Grand Challenge was in 2004. This was the first self-driving car challenge by the Defense Advanced Research Projects Agency in the United States. It was just 7 years later, in 2011, that Google introduced self-driving cars. It's now 2024, 13 years since then. Where are they? And the answer is, well, there are self-driving taxis in San Francisco and a few other places in the country, in the United States. But in general, they're not here. And, if you ask me where's the last place on earth where self-driving technology will finally work, it's going to be India, as you know. I mean, when I've been driving in India, I find it very an interesting experience. I find crossing the street there to be a terrifying experience, actually, and I don't understand how people can do it. But I always find myself dashing across the street, like I'm running a race. So it just takes a lot longer to get there. And so, this is the learned or built-in thing. Here's another example of the last mile is the hardest. I asked ChatGPT, admittedly 3.5, to tell me about myself. Tell me about Larry Birnbaum, a professor of computer science at Northwestern. Here's what it says. Larry Birnbaum was a professor of computer science at Northwestern University. He earned his bachelor's degree in mathematics from Harvard University and his PhD in computer science from Stanford University. This is false. I went to Yale University both as an undergraduate and a graduate student. That's why I call this is me in a parallel universe. This could have been me, but it's not me, okay? It says I'm a member of the Artificial Intelligence and Advanced Computing Center, the Data Science Institute, and the Cybersecurity Center at Northwestern. The first two of these don't exist. The second one does exist, but I'm not a member of it. The next line about what my research is correct. I have published extensively in the field of computer science. I have not written several books, however. I've written more than 160 journal articles and conference papers. I have not received any of these awards, and it also doesn't mention any of my numerous patents. So, this is actually like I said, this could have been me, but it's not me. And this is really a challenge. Here's my next challenge. This is what I'm working on right now, taking your order at McDonald's. I would like to use LLMs for this task. And it turns out that if the order is straightforward, it's easy. So in other words, if this order looks like I want a quarter pounder small fries and a large Diet Coke, then GPT-4 Claude and Gemini are all highly accurate, 97 to 100% accurate in generating a correct JSON representation of this order with a reasonable prompt. That prompt being, what's the menu and what does the JSON look like? However, if I have a more realistic example, I want a quarter pounder small fries and a large Diet Coke. Wait, large fries and oh yeah, no pickles. Accuracy drops substantially to an average of less than 69%. So this is not a solved problem by any means. And what I'm looking into now is why doesn't this work? Because obviously I want to fix this. And to be clear about what has to go on here is, what do you need to understand this order? You need to understand that the user is making a change. What is the nature of the change? Is it an addition, a deletion, or a modification? If it's a modification, which item is being modified? Which attribute or field of the item is being modified? And what is the new value of that field? So there's 5 things you need to understand this amended order, okay? And you might be more or less explicit about this. For example, here's a complicated order. I want a quarter pounder, a small vanilla shake, and a small fries. Make that chocolate. All that's being provided explicitly, we all understand that what this means is I want a small chocolate shake instead of a small vanilla shake, okay? But all that's being explicitly provided is the new value of some field of some item. The user or the system needs to infer that the user wanted to make a change, that the change is a modification as opposed to an addition or a deletion, that the item being modified is the shake, and that the field being modified is the flavor. We know this because the only thing that chocolate could pertain to is the flavor of the shake in this entire order. But the rest has to be inferred, and it turns out to be not that easy to infer it. And so this might seem like a very simple challenge, but actually LLMs, for all their genius, can't do it. And that's kind of where I'm working now. How do we make them useful in this task? So I want to thank you for your time and for your patience today. I apologize again for the fumble at the beginning and for going over in my time. I hope I've given you some food for thought about how to build applied AI systems that will work in the real world, and how to use different kinds of engineering techniques to build those systems, not just LLMs, although if LLMs are the right thing to use them for sure. And here I want to thank all of my students and colleagues over the years and the people who funded my research. And thank you all again for your time today.
Thank you, Dr. Birnbaum. I guess we can just spare 1 or 2 minutes for a quick Q&A session. Participants, feel free to ask away your doubts and questions. Anyone?
No problem. Go. Yeah, please. Yes, hello.
I'm Sushant from Maharashtra, sir. I'm working as a assistant professor in Women's College, Siddheshwar Women's College. My question is not about.
I'm sorry. In Maharashtra, you said?
Yeah, near Mumbai, sir.
Okay, good.
Sholapur. Yeah. So my question was not a technical perspective. I just want to grab this opportunity to ask you a question, because you have a huge amount of experience, like 38 years in educational field. So I just wanted to ask you what do you think about the education system in India and in US? Because what we are facing problem in the India is we are creating like a job. More students are like job takers, not job givers. So, but what I just by seeing your presentation, it's obvious that the education system in your US and the energy which you are talking like is is 5 times more than me. I mean, my age is less than your experience. But
don't sell yourself short. I mean, look, first of all, that's my temperament, and everybody has. I'm sorry.
Yes, sir. Yeah.
So first of all, I mean, different people have different temper. Can you hear me or not hear me?
We can hear
Sorry,
you.
it's a noise. It's a noise.
Oh, okay. So first of all, different people have different temperaments, and there's different approaches to getting work done in the world. And so, you know, I'm a kind of an excitable fellow, and so if I seem like I'm shouting a lot, that's just my nature. I do get excited about my work, but I think plenty of low key people got a lot of great work done in the world as well. So I wouldn't be. Look, I think that there are differences. I did find differences teaching in India and teaching in the United States. And we can talk about some of those differences. But I think I don't want you shouldn't overestimate how good the educational system in the United States or anywhere else in the world is. You know, I think the reality is that you know, there's a lot of rote memorization that goes on everywhere, and especially in the pre-college levels in the United States as well as around the world. And I don't think this is conducive to teaching people how to think for themselves, for sure, or how to solve problems very well. You know, I have a lot of criticisms of my own education and even of the education I sometimes offer my students. I do try to teach them how to ask questions, which I think is the most, the reality of doing research is asking the right question is like, 80% of the challenge. You know, you have to ask a question that's focused enough that it's possible to answer, that it's relevant to the big question you care about, and it's small enough to actually do something about it. And that's still a kind of a skill or an art, not something, which is why research is taught, by the apprentice method in graduate school, not just through classes. This is because we don't know any other way to teach it yet. Perhaps LLMs will be able to teach people how to do this. It's a serious problem all around the world, I think. Kind of not teaching kids how to think for themselves, not teaching them how to recognize that there is a problem or how to solve a problem. And I see this in the United States as well as everywhere else. So I'm not going to, I wouldn't, I think there are differences in India. The scale of the country is so vast. And although, I'm amazed and impressed by the dynamism of India every time I'm there and how far it's come. I didn't visit until a few years ago. So, but, looking at the numbers, you can see how much wealthier it is now than it was even 20 years ago. And that trend will only continue. And that's a wonderful thing. And with that will come, a better education and more educational opportunities. I do fear that the problem that there's there's one thing I do want to comment on, which I think the level of competition in India is so fierce. It's such a large country, and the opportunities, unfortunately, because of the economy is relatively smaller compared to the size of the population, maybe seem somewhat limited. And the result is, this tremendously fierce competitive situation. And especially when you combine that with the use of standardized exams, you end up with these kind of situations where students feel that they're obligated to spend all their time cramming for these tests. And I know this is true in India. It's true to a certain extent, a lesser extent in the United States as well. And I don't think that's very conducive to learning. And the result, I think, we're the beneficiaries of this. I mean, I have wonderful colleagues who were, undergraduates at IIT Madras or IIT Kanpur, and and then came to the United States for graduate school and decided to make their home here. And I'm proud to have them as my colleagues and friends, and they're fantastically smart and talented people. But I can see also that this has led to a certain distortion, where people end up spending a year or two or more cramming for these exams, which I don't think is a productive use of time. And I don't know what to do about that. That's, I think, a function of the economic circumstances of the country. And I believe it will get better as the country becomes wealthier and there is more opportunity for people. So I think that's a problem that I hope will fix itself over time. And I have no recommendation for how to fix it. But yeah, that's definitely a difference. And you know, if I can say something maybe a little more controversial, there's a fair amount of cheating in the United States among students, and it's not getting any better, that's for sure. But you know, in India, I was a little bit surprised by how you know, in the United States, if people cheat and they're caught, they're pretty embarrassed or worse. I mean, it typically can lead to very bad repercussions in the U.S. If you're caught cheating, you know, you'll flunk the class or even be expelled from school if you're egregious enough. In India, to some extent, I found that students were somewhat shameless about it, to be honest. I mean, and their position was roughly, I know that everybody else is going to do it, and so what choice do I have? And I understand that point of view, but it really it did bother me a little bit. And but again, I think that that's something that will be fixed as the place becomes a little bit less cutthroat in its competition. This may not have been the answer that you were expecting, but this is kind of my thinking on the subject.
Yes, sir. Thank you. Thank you. And I just want to give you a compliment because I'm also in this field. I'm young, but the teaching energy which you have, even I don't have that kind of energy, sir. So it is very incredible, sir, at this age.
Well, that's very sweet of you. I'm actually talking about my own work, and you know, I'm kind of like lots of people. I'm a little bit narcissistic, and I'm excited about my own work. You'll notice I didn't give a lecture about somebody else's work, and believe me, I'd be a lot more low energy if I were doing that. So, but thank you very much for your kind compliment.
Yes, sir. Thank you.
Anything else, or is it time to quit?
Ron?
Yes, sir. So I guess there are no more questions. Okay, so as this informative session draws to a close, I have no doubt that each of us has learned a great deal about this quickly developing profession. We have been skillfully led by Dr. Larry Birnbaum through the possibilities in developing intelligent interactions across the various AI platforms. Especially in this day and age, there are 100 different software tools out there. But the important thing is, as Dr. Birnbaum said, about picking the right tools. The examples of his students' projects, I'm sure, has impressed us all. I must say, sir, I personally love the local Savvy as well as the Spectrum project. It really is important to view a story from different perspectives. All the other projects too, compare and contrast, book recs, local recs, all of them were wonderful examples. It helped us all to understand building intelligent interactions. We now know about the innovative methods advancing AI and how these developments are changing both academics and industry. And of course, Dr. Birnbaum, I'm going to take this chance to say that we at the St. Joseph's College are looking forward to a future collaboration with you. Now, I would like to invite the session chair, Professor Jacob Thomas, to present a virtual memento to Dr. Larry Birnbaum.
Well, thank you. First of all, thank you for your kind words and for the invitation, and thank you to St. Joseph College for sponsoring this.
Thank you, sir.
We sincerely thank Dr. Larry for sharing his knowledge with us today. Your session was truly inspiring. As a token of our appreciation, we would like to present you with a virtual memento. This is a small gesture to express our gratitude for your valuable time and effort. Thank you, sir.
Thank you very much. And have a pleasant evening to all of you, and as I face my new day.
Thank you, Professor Jacob Thomas, for organizing this session and ensuring that everything ran smoothly. Your hard work is greatly appreciated. A heartfelt thank you once again, Dr. Larry, for sharing your expertise with us today. We give out a special thank you to Professor Lakshmi Ji for her valuable contributions to this session. Finally, to all the participants, I would like to extend my deepest gratitude for your active participation throughout this session. Your enthusiasm and engagement is truly appreciated. We'll now be sharing a feedback form in the chat, and the WhatsApp group shortly. Please take a few minutes to fill it out using your participant ID. It is essential for marking attendance for the event. You can find the participant's ID in the WhatsApp group where it has already been published.
And thank you again. I will take my leave now, okay?
Thank you, Doctor.
Thank you, sir.
Thank you all once again for being part of this enriching experience. We look forward to seeing you all again for tomorrow's session. Wishing you all a pleasant evening and a good night. You may now leave the call at your convenience.
Excuse me, sir. Hello. Hello.
Yes,
Hello.
sir. Yes, sir.
Sir, I filled the attendance using ATAL ID and not the ID that you have published. Will it make any problem, sir? Hello.
So could you repeat the question?
I have filled all the attendance using ATAL ID and not the ID that you have published.
One participant ID is published in the WhatsApp group. Are you a member in the WhatsApp group?
Yeah, I am the member. Actually, I saw it late. So actually, I thought ID means ATAL ID. So actually, I wrote ATAL ID.
Yeah. Your good name, please.
Atul B. Rao.
Okay, I will note it during the my attendance marking. Okay.
Yeah, for all the attendance, I entered ATAL ID.
Okay. I will note it. I noted it, and I will handle it during the attendance marking. Okay.
Okay, sir. Thank you, sir. Thank you.
Okay.
Sir, good evening, sir.
Yes, good evening.
Sir, myself, Dr. Sunil, sir. I'm daily attending the FDP, sir, but my attendance was not updated in ACT portal.
No, you don't want to worry. It will be updated in the end of the sessions, all sessions, 13 sessions. Okay.
Okay. After completion of all the sessions.
Yeah.
Okay. Thank you, sir. Thank you.
Okay.